Every night without fail, it rises. Not with fanfare, not with noise. It simply appears at the edge of the world, pale and luminous, climbing slowly into the dark sky above you. You have seen it thousands of times. You grew up beneath it. You have watched it hang over cities and deserts, over oceans and mountains, over sleeping neighborhoods and quiet fields. It is so familiar that most nights you barely notice it at all. And yet, that soft light falling across your window right now has traveled nearly 400,000 kilometers to reach you. It left the surface of another world, bounced off ancient rock that has not been touched by wind or rain in billions of years, crossed the silence of space, filtered through Earth's atmosphere, and arrived here, gently, without asking for your attention. The moon, Earth's oldest companion, the most visited object in the night sky, and perhaps the least truly seen. Take a moment, if you can, to simply imagine it above you. Not the idea of the moon, not the symbol or the metaphor or the romantic image from 1,000 songs and poems. The actual object, a sphere of rock and dust, 3,474 kilometers across, orbiting our planet at an average distance of 384,400 kilometers. It has no air, no wind, no weather. Its surface has not changed in any meaningful way for hundreds of millions of years. The same craters that early astronomers sketched by candlelight are there right now, exactly where they have always been. And somehow, despite all of that, despite being a cold, airless, geologically quiet ball of ancient stone, it has shaped nearly everything about the world you live in. The tides that carve coastlines, the length of your days, the stability of your seasons, the very fact that life on Earth had enough time and calm to grow complex enough to look up and wonder about the sky, all of it carries the quiet fingerprints of the moon. That is not poetry, that is science, and over the next few hours we are going to explore it together. Humanity has always known the moon was special, even when we had no idea why. For tens of thousands of years, long before telescopes or mathematics or the concept of gravity, our ancestors tracked the moon the way we might track a trusted friend. They watched it grow from a thin silver crescent into a full glowing disk, then shrink back into darkness, then return again. Reliable, predictable, unlike almost everything else in a world that must have felt wildly unpredictable. Ancient Egyptians saw in the moon the god Thoth, keeper of time, wisdom, and the balance of the cosmos. In Mesopotamia, the lunar god Sin was considered more powerful than the sun, because the moon could be seen even in daylight, moving through the sky with calm authority. The ancient Greeks gave the moon a goddess, Selene, who drove a silver chariot across the night sky. The Romans called her Luna, the word that still lives inside the English language today, hidden inside words like lunatic and luminous and lunar. Across every culture, on every continent, people looked up at the same object and felt the same pull, not just wonder, something deeper, a sense that this light in the darkness was connected to them, to their crops, their bodies, their calendars, their dreams. They were more right than they knew. Before we go further, there is something worth pausing on, something so visually striking that it has fascinated scientists and philosophers alike for centuries. When you look at the moon in the sky, particularly when the sun is also visible, the two objects appear almost exactly the same size. Not roughly the same, not approximately the same. So precisely the same that during a total solar eclipse, the moon fits over the sun like a key in a lock, blocking the light almost perfectly and revealing the sun's corona, that ghostly halo of plasma, in a way that would be impossible if either object were even slightly larger or smaller in apparent size. This is not a coincidence in the casual sense of the word. It is a numerical coincidence of remarkable precision. The sun is approximately 1.39 million kilometers in diameter. The moon is 3,474 kilometers in diameter. The sun is roughly 400 times wider than the moon, and the sun is roughly 400 times farther away. Those two numbers cancel each other out so cleanly that from the surface of Earth, the two objects appear almost identical in size. No other planet in our solar system has a moon that creates this kind of perfect visual alignment. No other known world offers its inhabitants a total solar eclipse quite like ours. What does that mean? Perhaps nothing, perhaps everything. Scientists are careful not to read too much into numerical coincidences, but it is worth sitting with the fact that the universe arranged things in such a way that the one species on Earth capable of appreciating total solar eclipses happens to live on the one planet where they occur so perfectly. There is no explanation for this, only the quiet wonder of noticing it. The moon has another visual trick that deserves a moment of attention, because it is something almost everyone has experienced and almost no one can fully explain. When the moon sits low on the horizon, just risen or about to set, it looks enormous, swollen, almost impossibly large, as if it has swelled during its journey across the sky. And then, a few hours later, when it hangs high overhead, it seems to have shrunk back to its usual size. This is called the moon illusion, and it is entirely in your mind. Measurements confirm what seems impossible. The moon is actually slightly smaller in angular size when it is near the horizon than when it is directly overhead, because you are standing on a curved planet and the moon is a tiny fraction farther away at the horizon. And yet it appears larger, dramatically larger to most people. The most widely accepted explanation involves the way human brains interpret distance and size together. When the moon is low in the sky, surrounded by trees and buildings and the visible horizon, your brain unconsciously uses those familiar objects as reference points and concludes that the moon must be very far away and therefore very large. When the moon is high overhead, those depth cues disappear and your brain reassesses. In other words, the moon that looks so breathtaking as it rises, that great golden harvest moon hanging just above the rooftops, is a painting your own mind is creating. You are not seeing the moon more clearly in that moment. You are seeing your brain's interpretation of it. And somehow that makes it no less beautiful. Close your eyes for a moment if you are comfortable doing so. Picture the moon as it appears tonight or as you last remember it. Let it hang there in the dark behind your eyelids, that soft light, that ancient surface, that impossible familiarity. We have been looking at this object for our entire existence as a species. Our earliest ancestors painted animals on cave walls by its light. Sailors navigated oceans using it as a clock and a compass. Farmers planted crops according to its phases. Poets wrote about it in every language ever spoken. Children reach for it from cribs. And yet we are only beginning, in the long story of human understanding, to appreciate how deeply it is woven into the fabric of Earth itself. How it is not merely a beautiful object above us, but a structural part of the system that made us possible. The moon did not just light the night for our ancestors. It helped create the conditions in which those ancestors could exist. To understand how, we need to go back, much further back than human history, further back than life itself. We need to travel to a time when Earth was young and the solar system was a far more violent and chaotic place than it is today. We need to understand what the sky looked like before the moon was there. There is a number that keeps appearing in the relationship between Earth and the moon. Not approximately, not roughly, with a precision that stops astronomers mid-sentence when they first encounter it. The sun is 400 times wider than the moon. The sun is 400 times farther away than the moon. Two completely unrelated measurements, the physical size of one object and the orbital distance of another, producing the same number, as if the universe were following a script. We touched on this briefly at the end of our last passage, but it deserves its own space, its own silence, because when you sit with it long enough, it becomes one of those facts that quietly rearranges something in the way you see the world. To feel the full weight of this coincidence, it helps to understand the scale involved. The sun is not merely large, it is almost incomprehensibly large. Its diameter stretches approximately 1.39 million kilometers, wide enough to fit 109 Earths side by side across its face. If the sun were the size of a front door, Earth would be roughly the size of a coin, and the moon, in that same scale, would be a small marble. Now step back far enough from that front door that it appears the same size as the marble. That is the distance you would need to stand from the sun for it to look the same size as the moon does from Earth's surface. That distance is approximately 150 million kilometers. That is where we are, that is where Earth sits in its orbit. And from this precise location, not from Mars, not from Venus, not from any other position in the inner solar system, the two objects match. One small marble, one enormous door, seen from exactly the right place. The consequences of this alignment are more significant than they might first appear. A total solar eclipse is not merely a visual spectacle. For most of human history, it was one of the most powerful scientific tools available to us. When the moon slides perfectly in front of the sun, it does not simply block the light, it creates a natural laboratory. The sudden darkness reveals the sun's outer atmosphere, the corona, a vast, wispy structure of superheated plasma that is otherwise completely invisible against the brightness of the solar disk. For a few precious minutes during totality, scientists can observe the corona directly, study its temperature, its movement, its structure. Some of the most important discoveries in solar physics were made during eclipses. The element helium was first identified not on Earth, but in the sun's spectrum during a total eclipse in 1868, decades before it was found in terrestrial rocks. Early evidence supporting Einstein's theory of general relativity came from observations made during the total solar eclipse of 1919, when astronomers confirmed that the sun's gravity bent the light of background stars exactly as Einstein had predicted. None of those discoveries would have been possible without the coincidence. Without the moon being the precise apparent size it is, the corona would remain hidden behind the glare, and those windows of understanding would never have opened. It is a strange thing to consider that a numerical accident in orbital geometry may have accelerated human knowledge of the universe by decades. But here is where the story takes an unexpected turn. This coincidence is not permanent. The moon is not sitting still, it never has been. Right now, at this moment, as you breathe slowly and let these words wash over you, the moon is drifting away from Earth at a rate of approximately 3.8 centimeters per year, not dramatically, not visibly, but measurably, reliably, constantly. We know this because scientists have been bouncing laser beams off reflectors left on the lunar surface by Apollo astronauts since 1969. By measuring the time it takes for those pulses of light to return, we can calculate the Earth-Moon distance with extraordinary precision, and the data is unambiguous. The moon is slowly, steadily retreating. This means that in the distant past, the moon appeared larger in the sky than it does today. Ancient solar eclipses were not the same as ours. The moon would have more than covered the sun, creating a deeper, longer darkness, and in the far future, the moon will appear smaller. There will come a time when the moon is too distant to completely cover the solar disk, and total solar eclipses, as we know them, will become impossible. We happen to live in the narrow window of geological time when the match is nearly perfect. We will explore the moon's retreat in much more detail later in our journey, but for now, let it sit with you, the quiet improbability of the moment we inhabit. Every generation of humans who has ever lived has looked up at roughly the same moon, roughly the same size, in roughly the same relationship with the sun. And every generation that follows, for billions of years into the future, will see something subtly but irreversibly different. We are living in what may be the golden era of solar eclipses, and most of us will never once think about it. There is another aspect of this coincidence that deserves careful attention because it points to something deeper than mere visual symmetry. The moon's apparent size in the sky, that disk of roughly half a degree of arc, is not simply aesthetically pleasing. It represents a gravitational relationship. The same distance that makes the moon appear the size it does is also the distance at which the moon exerts the gravitational influence it does on Earth. And that gravitational influence, as we will discover in later sections, is responsible for the tides, for the stabilization of Earth's axial tilt, and for conditions that may have been essential to the emergence of life. In other words, the coincidence is not just visual. The size we see and the force we feel come from the same source, the moon's position in space. They are two faces of the same relationship. When you look at the moon tonight and appreciate how perfectly it seems to fit the sky, you are also, without knowing it, appreciating the precise gravitational distance that helped make your existence possible. Astronomers are generally careful about the word coincidence. Science prefers mechanisms to mysteries, explanations to accidents, and the honest answer is that there is no known reason why the numbers should align the way they do. It is not the result of any physical law. It is not evidence of design. It is simply a feature of the particular solar system we happen to inhabit, with its particular moon at its particular distance, orbiting its particular planet at its particular orbital radius. Other solar systems almost certainly have moons. Some may even have moons of roughly similar size relative to their planet. But the precise visual matching, the 400 and 400, appears to be nothing more and nothing less than chance. And yet, there is something philosophically interesting about the fact that the species capable of noticing this coincidence is the same species that lives on the only planet where it occurs. We are here, aware enough to be amazed precisely because this moon is at this distance. The coincidence did not just give us beautiful eclipses, it helped give us everything. That is not an argument for anything mystical or supernatural. It is simply an invitation to pause, to notice, to let the scale of it settle gently into the quiet parts of the mind before sleep. The universe did not have to arrange things this way. There was no requirement, no law, no inevitability. And yet here we are, beneath a moon that fits the sun like it was made to. But the moon we see tonight, this perfectly proportioned silver companion, did not always exist. There was a time, deep in the history of our solar system, when the night sky above Earth was completely, utterly empty. No moon, no tides, no stable seasons, just a young, violent planet beneath a star-filled darkness, hurtling through a solar system still in the chaos of its own formation. To understand where the moon came from, we have to go back to a time before it existed at all, to an early Earth that was almost nothing like the world we know. A world raw, molten, bombarded, and alone. And we have to witness one of the most violent events in the history of our solar system. To truly understand the moon, you must first imagine a sky without it. Not the sky you know, not the familiar darkness softened by that pale, steady glow. A sky that is simply black, absolute, unbroken by any companion world. Just stars, cold and distant, and a young Earth beneath them still finding its shape. This is not science fiction, this was reality. For the first tens of millions of years of Earth's existence, there was no moon. The night was darker than anything alive today has ever experienced. The oceans, if they existed at all, moved without tides. The planet tilted and wobbled through space with no gravitational hand to steady it. And the days were shockingly, almost violently short. We are going back approximately 4.5 billion years, before the first cell, before the first ocean, before the first breath of oxygen in the atmosphere, back to a solar system that was still in many ways a construction site. The solar system did not begin as the orderly, well-spaced arrangement of planets we know today. It began as a cloud. An enormous, slowly rotating cloud of gas and dust, the remnants of an earlier generation of stars that had lived and died long before our sun ignited. Over millions of years, gravity pulled this cloud inward. It collapsed under its own weight, spinning faster as it contracted, the way a figure skater pulls their arms inward and accelerates. At the center, material compressed until temperatures and pressures became extreme enough to trigger nuclear fusion, and a new star was born. Our sun. But not all of the cloud fell into the sun. A flat, rotating disk of material remained around it, dust and ice and rocky fragments and gases, all circling the young star in tight, chaotic orbits. This was the protoplanetary disk, the raw material of everything that would follow. Within this disk, small particles began to collide and stick together. Dust grains became pebbles, pebbles became boulders. Boulders became what scientists call planetesimals, objects kilometers across, massive enough for their own gravity to begin pulling in more material. Over millions of years, these planetesimals grew larger and larger, sweeping their orbits clean, consuming smaller objects or flinging them outward. This process, called accretion, was not gentle. It was a slow-motion demolition Darby played out across hundreds of millions of years. Objects collided at tremendous speeds. Some shattered, some merged. The survivors grew massive. Eventually, in the region where Earth now orbits, one object grew large enough to dominate its neighborhood. We call it Proto-Earth, the early precursor to the planet we live on today. But Proto-Earth was nothing like the Earth you know. There was no blue ocean glittering in sunlight, no atmosphere rich with nitrogen and oxygen, no continents drifting slowly across a mantle of rock. Proto-Earth was a roiling, largely molten body, its surface a churning ocean of liquid rock, what geologists call a magma ocean, kept fluid by the constant energy of ongoing accretion impacts and the decay of radioactive elements within its interior. The sky above this early Earth, if you could have stood on its surface without immediately being vaporized, would have been thick and opaque. Volcanic gases poured endlessly from the interior. There was almost certainly no free oxygen. The sun, younger and somewhat fainter than it is today, would have barely penetrated the murky atmosphere. It was a hellish world by any human standard, and yet it was home, the only home our matter had ever known. And critically, it was alone. No moon hung in that ancient sky. No gravitational partner steadied the planet's tilt. No tidal forces rhythmically pulled at whatever liquids existed on the surface. The early solar system was also far more crowded than it is today. Between the Sun and the orbit of Jupiter, space was filled with planetary bodies of all sizes, some nearly as large as planets, others much smaller, all jostling for position in an environment still far from gravitational equilibrium. These objects crossed each other's orbits. They pulled at one another with gravity. They collided. Scientists now understand that in this early period, the giant planets, Jupiter and Saturn in particular, were not sitting quietly in their current orbits. They were migrating, moving inward and outward through the solar system, their enormous gravitational influence reshaping the trajectories of everything around them. This migration scattered smaller bodies like seeds thrown by a careless hand, sending some plunging toward the inner solar system, others hurling outward into the cold dark beyond Neptune. It was a solar system in constant, violent motion. And somewhere in this chaos, another planet was growing. Not where we might expect, not far from Earth as a distant neighbor, but sharing almost the same orbital path, a world of roughly the same neighborhood, growing in the same region of the disk, warmed by the same young sun. Scientists call it Theia. We do not know exactly how large Theia was. Current models suggest it was roughly the size of Mars, perhaps 10% of Earth's mass. Not enormous by planetary standards, but large enough to carry tremendous kinetic energy, large enough to matter enormously. For millions of years, Theia and Proto-Earth coexisted in something like an uneasy gravitational dance. Both were growing, both were accumulating mass from the disk material around them. Both were following orbital paths that from a distance might have looked almost identical. But the solar system in this era was not a place of stable coexistence. The gravitational influences of Jupiter, Saturn, and the other growing bodies were constantly tugging at the orbits of smaller worlds, introducing tiny perturbations, small deviations that, over millions of years, could grow into something significant. Slowly, inevitably, Theia's orbit began to shift. It is worth pausing here to appreciate what we are actually describing. We are talking about events that happened 4.5 billion years ago, on objects that no longer exist in their original form, in a solar system that looked nothing like the one we inhabit today. No human was there. No instrument recorded what happened. There are no photographs, no written records, no witnesses of any kind. And yet we know, with reasonable scientific confidence, roughly what occurred. We know it from the chemistry of moon rocks brought back by Apollo astronauts. We know it from computer simulations that model the behavior of planetary bodies under known laws of physics. We know it from the isotopic signatures of oxygen and other elements that tie the moon's composition intimately to Earth's own mantle, as if the two bodies were once a single thing. Science does not always give us certainty, but it gives us something remarkable: the ability to reason backward through time, to read the present as a record of the past, and to reconstruct events that no eye has ever witnessed. And what those methods tell us about the origin of the moon is both violent and beautiful. Theia is approaching. Not quickly by human standards, not in any way that any hypothetical observer could have perceived from moment to moment. Orbital mechanics are slow, measured in the patient language of millions of years. But the trajectory is set. The gravitational dice have been cast. Two worlds that grew up in the same region of the same solar system, from the same cloud of ancient dust, are on a path toward each other that nothing in the universe will alter. Proto-Earth turns slowly beneath its opaque volcanic sky, warmed from within by the heat of its own formation, unaware, if a planet can be said to be unaware, of what is coming. Something is approaching from the darkness. And when it arrives, nothing will ever be the same. Let that thought drift with you into stillness. The collision is coming, and from it, something extraordinary will be born. It begins with a tremor. Not a sound, there is no air to carry sound across the void of space. But if you could somehow feel the fabric of gravitational forces shifting in the region where Earth orbits the young sun, you would sense something changing, a growing tension. Two massive bodies, each carrying the accumulated weight of millions of years of planetary formation, drawing closer to an encounter that has been mathematically inevitable for longer than either world has fully existed. Theia is coming. And in astronomical terms, it is almost here. Imagine for a moment the scale of what is about to happen. Theia is not a rock, not an asteroid, not the kind of object we might casually picture when we hear the word collision. It is a planet, a fully formed, differentiated planetary body, meaning it has already separated into layers, with heavier iron and nickel sinking toward its core and lighter silicate rock floating toward its surface, just as Earth has done. It has its own geological history, its own interior heat, its own gravity strong enough to hold itself into a sphere. It is, by any reasonable definition, a world. And it is approximately the size of Mars, somewhere between a third and a half the diameter of Proto-Earth, with perhaps 10% of Earth's total mass. In human terms, that mass is so large as to be essentially meaningless as a number. In planetary terms, it is a mid-sized impactor, large enough to cause global catastrophe, but not so large that it simply obliterates everything outright. The angle of impact matters enormously in what follows. Current models suggest Theia did not strike Proto-Earth head-on, like two billiard balls meeting directly. Instead, the collision was oblique, a glancing blow, a side-on impact, the kind that transfers enormous energy while also imparting a tremendous rotational spin to the combined system. That detail will turn out to be everything. The impact itself unfolds over a timescale that is, by cosmic standards, almost instantaneous. In the seconds and minutes of first contact, the crusts of both worlds begin to interact. Rock that has spent millions of years slowly cooling and solidifying is suddenly subjected to pressures and temperatures that exceed anything in its geological experience. The boundary between the two objects becomes meaningless almost immediately. There is no clean collision, no bouncing apart. At the speeds and scales involved, rock behaves less like a solid and more like a fluid. Theia does not simply strike Earth and stop, it plows through. Its momentum carries it deep into Proto-Earth's body, its iron core driving inward, the two interiors beginning to merge in a process of almost unimaginable violence. The energy of impact, kinetic energy accumulated over millions of years of orbital motion, converts instantly into heat. Temperatures at the impact site spike to levels comparable to the surface of the Sun. Both worlds, in any meaningful sense, cease to exist. What remains in the first hours after impact is something that has no good name in ordinary language. A rapidly rotating, partially vaporized mass of rock and metal and superheated gas, the merged remnants of two planets, spinning so fast that its day lasts only a few hours. Around this central mass, a vast disk of ejected material spreads outward into space, vaporized rock, molten droplets, solid fragments, all launched into orbit by the violence of the collision. The sky, if the concept of sky means anything in this moment, is a ring of glowing debris. This is the giant impact hypothesis, and for all its drama, it is not a fringe theory or a speculative guess. It is the leading scientific explanation for the moon's origin, supported by multiple independent lines of evidence that have accumulated over more than 5 decades of research. The most compelling evidence comes from the moon rocks returned by Apollo astronauts between 1969 and 1972. When scientists analyzed these samples and compared them to Earth's own mantle rocks, they found something striking. The isotopic ratios, the precise proportions of different atomic variants of elements like oxygen, titanium, and silicon, were nearly identical between Earth and Moon. Not similar, nearly identical. This is unusual. Objects from different parts of the solar system tend to have different isotopic signatures because they formed from slightly different mixtures of material at different distances from the Sun. Mars rocks have different isotopic ratios than Earth rocks. Asteroids have different ratios still. The solar system is not isotopically uniform. But Earth and Moon share ratios so similar that the simplest explanation is that they formed from the same reservoir of material, that the Moon is, in a very real sense, made of Earth. The giant impact hypothesis explains this elegantly. When Theia struck Proto-Earth, the material that was flung into orbit to eventually form the Moon came predominantly from Earth's own mantle, the outer layers of Proto-Earth that were disrupted and ejected by the impact. Theia's own material was largely incorporated into the merged central body that became the Earth we know. The Moon, therefore, is not a captured object from elsewhere in the solar system. It is not a companion that formed independently nearby. It is a piece of our own planet, flung into orbit by the most violent event in Earth's history. We are, in a very literal sense, looking at part of ourselves every time we look at the Moon. The hours and days after the impact are almost impossible to picture. The merged Proto-Earth is spinning rapidly, far faster than Earth spins today. Days last only 5 or 6 hours. The surface is entirely molten, a global magma ocean kilometers deep, glowing with an intense reddish heat that would be visible from space. Above this churning surface, a thick atmosphere of vaporized rock, silicate vapor, blankets the planet, trapping heat, keeping temperatures extreme. And overhead, still close, still partially fluid, the debris disk is already beginning to evolve. Within this disk, the same process that built the planets in the first place is beginning again, on a much smaller scale and a much faster timescale. Particles are colliding, clumping, growing. The stronger gravitational pull of larger clumps draws in more material. Within decades, perhaps centuries, a dominant object begins to emerge from the chaos of the disk. Something is forming in orbit around Earth. Something that will, over millions of years, cool and solidify and settle into a stable orbit. Something that will, over billions of years, reshape the oceans, steady the planet's tilt, slow Earth's rotation, and make itself so fundamental to the conditions of life that its absence is almost impossible to imagine. It is still just debris right now, just a ring of molten rock orbiting a glowing, spinning world. But it is becoming the Moon. There's something quietly profound about this origin story. The moon was not placed here. It was not a gentle gift from a well-ordered universe. It was born from catastrophe, from the death of one world and the near destruction of another, from collision and chaos and unimaginable heat. And from that violence came something that would, billions of years later, hang softly in the night sky above sleeping cities, casting gentle light through bedroom windows, pulling gently at the oceans, steady and calm and seemingly eternal. Destruction and creation are not opposites in the universe. They are, very often, the same event seen from different distances in time. Let that thought settle softly as you rest. From fire and collision, something beautiful was forged, and next we will watch it cool. The chaos is beginning to quiet. Not quickly, not in any way that could be observed from moment to moment, even by the most patient watcher. But the laws of physics are patient in ways that living things cannot fully comprehend, and they are already at work, sorting, cooling, organizing the violence of the impact into something new. The debris disk that encircles the young, wounded Earth is still glowing, still partially vaporized, still a swirling, chaotic ring of silicate droplets and rocky fragments and superheated gas, all moving in rough elliptical paths around a planet that is itself still molten, still spinning too fast, still radiating the heat of its own catastrophic birth. But gravity does not rest, and gravity, given enough time, is the most patient architect in the universe. Within the debris disk, something familiar is beginning to happen. The same process that built proto-Earth from dust and gas, accretion, the slow gravitational gathering of small things into larger things, is now playing out again, compressed into a much smaller region of space and running on a much faster clock. In the outermost regions of the disk, where temperatures are slightly lower and material has had more time to cool, tiny particles of condensed silicate rock are beginning to stick together. Dust becomes grains, grains become clumps, clumps become boulders, and boulders, drawn together by their own modest gravity, begin to merge into something larger still. Computer simulations of this process, run by planetary scientists who have spent careers modeling the aftermath of the giant impact, suggest that the moon did not take long to form by geological standards. Not millions of years, not even hundreds of thousands. Within perhaps a few thousand years of the initial collision, the bulk of the lunar mass had already gathered itself into a single dominant body. In cosmic terms, the moon assembled almost overnight. But what emerged from that rapid accretion was nothing like the moon we see today. The early moon was close, far closer than it is now, perhaps only 20 or 30,000 kilometers from Earth, compared to the current average of 384,400 kilometers. From Earth's surface, it would have appeared enormous in the sky. Not the modest disk we know, but a swollen, overwhelming presence, perhaps 15 or 20 times larger in apparent size than the moon we see tonight. And it was hot. Extraordinarily, almost incomprehensibly hot. The energy released during the accretion process, all those collisions between fragments of rock and metal, all that kinetic energy converting to heat, kept the young moon's surface and much of its interior in a molten state. Scientists call this the lunar magma ocean. It was not a metaphor or an approximation. The moon's outer layers, perhaps hundreds of kilometers deep, were a true ocean of liquid rock, glowing with intense heat, churning slowly as convection currents moved through it. If you could have hovered above the early moon in those first millions of years, protected somehow from the radiation and heat, you would have looked down on a world that appeared almost alive. A surface of slowly moving, glowing orange and red, punctuated by brighter regions where hotter material welled up from below. No craters yet, because any impacting object would simply be swallowed into the melt. No mountains, no highlands, just an undulating, luminous ocean of molten silicate rock stretching from pole to pole. Below it, slowly sinking toward the center, the heavier elements were finding their way downward. Iron and nickel, denser than the surrounding rock, descended through the magma ocean toward the moon's core. Lighter elements, aluminum, calcium, sodium, rose upward, accumulating near the surface. The moon was sorting itself out, differentiating, becoming layered, becoming, in the most fundamental geological sense, a world. The cooling process was gradual but relentless. As the young moon radiated its heat into the cold of space, the magma ocean slowly began to solidify from the outside inward, and, in certain regions, from the inside outward as well, as the deep interior cooled under pressure. The first solid minerals to crystallize from the cooling melt were dense, iron and magnesium-rich silicates, minerals that, being heavier than the surrounding liquid, sank downward, adding to the growing solid mantle beneath the magma ocean. But then something interesting happened. As crystallization continued, the remaining liquid in the magma ocean became increasingly enriched in elements that did not fit easily into the crystal structures of the common minerals forming around them. Aluminum, calcium, and a mineral called anorthosite began to crystallize, and anorthosite, crucially, is less dense than the surrounding magma. Instead of sinking, it floated. It floated upward through the slowly cooling magma ocean and accumulated at the surface, forming a solid crust. That ancient anorthosite crust is still there today. When you look at the moon with the naked eye and see the bright, pale regions, the lunar highlands, the rugged terrain that covers much of the moon's surface, you are looking at rock that crystallized from the lunar magma ocean more than 4 billion years ago. You are looking at the moon's original skin. The bright lunar highlands are, in a very real sense, the oldest visible surface in the inner solar system, older than any rock on Earth, older than any landscape you have ever seen or will ever see on this planet. They have been there, largely unchanged, for almost as long as the solar system itself. The cooling took time. Perhaps 30 to 50 million years passed before the lunar magma ocean fully solidified, an enormous span by human reckoning, but a brief adolescence by geological standards. During this time, the young moon was also being bombarded. The early solar system was still littered with leftover debris from the planet formation process, asteroids, comets, rocky fragments of all sizes still crossing the orbits of the newly formed worlds. The moon, with no atmosphere to burn up incoming objects and no geological activity to erase the evidence, received them all directly. Every impact left its mark. But in these early years, with the surface still partly molten or freshly solidified, many of those impact craters were erased almost as quickly as they formed, swallowed by the still warm crust, smoothed over by the last remnants of volcanic activity. The moon was healing its own wounds almost as fast as they appeared. That would not last. As the interior cooled further and volcanic activity diminished, the crust hardened completely, and the bombardment continued. The craters that formed in this later period, and especially during a particularly intense episode of impacts called the Late Heavy Bombardment, which occurred roughly 3.9 billion years ago, are the ones that survive today. The Great Basins, the ancient highlands, the overlapping rings of impact craters that give the moon's near side its familiar, cratered face. Each of those craters is a scar, a memory, a record of something the moon endured and survived. There is a stillness that comes with understanding this history. The moon above you tonight is not simply a rock in orbit. It is a geological archive, the most complete and ancient record of the early solar system available to us, precisely because it lacks the atmosphere, the tectonic activity, and the liquid water that have erased so much of Earth's own early history. Earth has been continuously rewriting itself for 4.5 billion years. Plates have collided and subducted, oceans have formed and evaporated, erosion has smoothed away mountain ranges that once rivaled the Himalayas. Almost nothing on Earth's surface is more than a few 100 million years old. The moon remembers what Earth has forgotten. In its ancient highlands and its great impact basins, in the chemistry of its rocks and the structure of its crust, the moon holds a record of conditions that existed before life, before oceans, before the atmosphere we breathe. It is a window into a time that is otherwise almost entirely lost to us. And now, slowly, the young moon begins to settle. The magma ocean is solid, the crust has formed, The great bombardment is winding down. The moon is moving into a quieter phase of its existence, still geologically active in places, still warm inside, but no longer the glowing, churning world of its violent youth. It is becoming recognizable, becoming permanent. And as it settles into its orbit, a subtle but profound gravitational conversation between Earth and Moon is beginning, one that will, over millions of years, lock the two worlds together in a relationship unlike any other in the solar system. The Moon is about to stop turning its back on us. Rest in that stillness. The Moon is cooling, settling, finding its place, and in our next passage, we will discover why it always shows us the same face. There is something you have never seen. You have looked at the Moon hundreds of times, perhaps thousands, as a child, as an adult, from different cities, different countries, different seasons. You have seen it full and bright, a perfect silver circle hanging in the darkness. You have seen it as a thin crescent balanced on the horizon at dusk. You have seen it pale and ghostly in the middle of a blue afternoon sky. But in all of those viewings, across your entire life, you have only ever seen one side of it. The same craters, the same dark patches, the same ancient face turned toward you with a stillness that never wavers. The Moon rotates, it does spin on its axis, slowly and steadily, and yet from Earth, we never see the result of that rotation. The face it shows us today is the same face it showed the first humans who looked up at the night sky. The same face it will show the last humans who ever do. This is not a coincidence. It is not an accident of geometry. It is the result of a deep gravitational process that took hundreds of millions of years to complete, and it tells us something fundamental about how the Moon and Earth are connected. To understand why the Moon always shows the same face, it helps to start with a simpler question. Why does anything rotate at all? When the solar system formed from its swirling disk of gas and dust, everything in that disk was moving, orbiting the young sun, drifting, colliding. When objects merged together through accretion, they carried with them the combined rotational momentum of everything that had gone into them. The result was that virtually every object in the solar system, every planet, every moon, every asteroid ended up spinning to some degree. Rotation is the default state of things in space. The early Moon was no exception. Freshly formed from the debris of the giant impact, it inherited a spin rate from the dynamics of its own accretion. In its youth, the Moon rotated freely, completing a full turn on its axis at a rate independent of how long it took to orbit Earth. If you had been able to watch from a fixed point in space in those early eons, you would have seen the Moon slowly turning, showing its entire surface to the universe. But Earth was watching too, and Earth's gravity had something to say about it. Here is the key to everything that follows. The Moon is not a perfect sphere. No natural planetary body is. The distribution of mass inside the Moon is slightly uneven. There are regions where denser material is concentrated, subtle variations in the thickness of the crust, asymmetries inherited from the violence of its formation, and the uneven pattern of its subsequent bombardment. This uneven mass distribution means that Earth's gravity does not pull on the Moon uniformly. It pulls slightly harder on the regions of the Moon that are denser, and slightly less hard on the regions that are less dense. And because the Moon is a large object, not a point, but a body with real physical extent, the side of the Moon facing Earth is also pulled slightly more strongly than the side facing away, simply because it is closer. These differential gravitational forces, what physicists call tidal forces, create a subtle but persistent torque on the Moon's body, a twisting force, and over millions of years, that twisting force did something remarkable. It gradually slowed the Moon's original rotation, bleeding away its spin one tiny increment at a time, until the rotation rate reached a very specific value. The value at which the Moon completes exactly one rotation for every one orbit around Earth. Think about what this means in practice. If the Moon rotates once on its axis in exactly the same time it takes to travel once around Earth, then from Earth's perspective, the Moon appears not to rotate at all. the same face is always pointed toward us. The same craters, the same dark maria, the same ancient highlands, always facing inward, toward the planet whose gravity shaped them into this permanent orientation. This state has a name. Scientists call it synchronous rotation or tidal locking, and it is far more common in the solar system than you might expect. Many moons of other planets are similarly locked to their parent bodies. The large moons of Jupiter, Io, Europa, Ganymede, Callisto are all tidally locked. So is Charon, the large moon of Pluto. So in fact is Pluto itself, locked to Charon in a mutual embrace where both bodies show the same face to each other at all times. Tidal locking is what happens when gravity and time are given enough of each other to work with. The moon simply got there first because it is close to a large planet, and close proximity makes tidal forces stronger. There is a beautiful symmetry hiding inside this process that is worth drawing out slowly. The same tidal forces that gradually slowed the moon's rotation are also, right now, gradually slowing Earth's rotation. The moon's gravity pulls on Earth's oceans and to a lesser extent on Earth's solid body, creating tidal bulges that, because Earth rotates faster than the moon orbits, are constantly being dragged slightly ahead of the moon's position. The moon pulls back on these bulges, trying to align them with itself, and this creates a subtle braking force on Earth's spin. The result is that Earth's days are slowly getting longer, not by any amount you would notice in a human lifetime. The lengthening is only about 1.4 milliseconds per century, but over geological time the effect accumulates dramatically. When the moon first formed, Earth's day was approximately 5 to 6 hours long. The rapid spin was a direct legacy of the giant impact. Over the subsequent 4.5 billion years, tidal braking has stretched that day to the 24 hours we experience today. And it is still lengthening, slowly, quietly, every century, every year, every day, imperceptibly longer than the last. Eventually, billions of years from now, if the sun does not intervene first, Earth's day will stretch until it equals the lunar month, just as the moon's rotation was locked to its orbit long ago. Earth and moon will face each other in a permanent gravitational gaze, each showing the same face to the other for all time. For now, though, the process is unfinished. We are partway through a cosmic dance that has been going on since the moon's formation and will continue long after we are gone. And what about the side we never see? For most of human history, the far side of the moon was one of the great mysteries of the natural world. Not because anyone doubted it existed, the geometry was obvious enough, but because no eye had ever seen it. No telescope on Earth could see around the moon's permanent orientation. No instrument could peer behind the face it always turned toward us. The far side was a blank, a question mark, a place that existed in mathematics and in imagination, but not yet in human experience. For thousands of years, philosophers and astronomers speculated about what might be there. Was it similar to the near side? Was it covered in vast dark plains like the lunar maria visible to any naked eye observer? Was it more heavily cratered or less? Did it harbor anything unexpected? The answer, when it finally came, was surprising in ways that nobody had fully anticipated. But that answer belongs to the next part of our journey. For now, it is enough to sit with the near side, the face the moon has always shown us, the face locked toward Earth by 4 billion years of patient gravitational conversation. That landscape of craters and highlands and dark ancient seas visible above you on clear nights is not just a geological surface. It is the face of a companion, a world that has oriented itself toward us so completely over so long a period of time that we have come to think of it as simply the moon's face, as if there could be no other. And in a human sense, there cannot be. No living person has ever stood on Earth and seen the other side. We have sent machines there and astronauts have glimpsed it from orbit. But from the ground, from the surface of this planet, the moon has one face and one face only. Turned always toward home. Let that thought hold you gently as you drift. The moon keeps its face toward us, faithful and still, and on the other side of that face lies a world that remained unseen for all of human history, until one small spacecraft changed everything. For all of recorded human history, it was simply unknown. Not unexplored in the way that distant continents were unexplored, where at least the possibility of reaching them existed, where ships could be built and winds could be followed and shores could eventually be found. The far side of the moon was unknown in a more absolute sense. Structurally, geometrically, permanently beyond reach, no ship could sail there. No telescope could see around the moon's locked orientation. No technology available to any civilization for thousands of years of human history could pull back the curtain on that hidden hemisphere. It existed in mathematics, it existed in logic. Every astronomer who ever lived knew with complete certainty that the moon had another side, but knowing something exists and being able to see it are two entirely different things. The far side of the moon was the last great hidden landscape of the natural world visible from Earth, and for most of human existence, it remained exactly that, hidden. The first hint that the far side might be different from what we see came not from any spacecraft, but from a subtle wobble. The moon's tidal locking is not quite perfect, because the moon's orbit around Earth is not a perfect circle but a slight ellipse. The moon moves a little faster when it is closer to Earth and a little slower when it is farther away. Its rotation rate, however, remains constant, turning at the same speed regardless of where it is in its orbit. This mismatch between orbital speed and rotational speed means the moon rocks very slightly back and forth over the course of each month, as if nodding slowly in its sleep. This rocking is called libration, and it means that over time, patient observers on Earth can glimpse slightly around the edges of the moon, catching brief, angled views of regions that would otherwise be permanently hidden. In total, libration allows us to see approximately 59% of the moon's surface from Earth, rather than the simple 50% that pure tidal locking would suggest. But the remaining 41%, the deep far side, the regions that libration never brings into view, stayed invisible. Until October 7, 1959. On that date, a Soviet spacecraft called Luna 3 completed one of the most consequential missions in the history of space exploration. Luna 3 was not large or sophisticated by modern standards. It was roughly the size of a large oil drum, carrying a camera system, a film processing unit, and a radio transmitter. It had no ability to land, no ability to collect samples, no ability to do much of anything beyond fly past the moon and photograph what it saw. But what it saw changed everything. As Luna 3 swung around the far side of the moon on a carefully calculated trajectory, its cameras activated and began photographing the surface in the light of the sun. The images were developed on board, using an actual photographic film processing system built into the spacecraft, and then scanned and transmitted back to Earth as radio signals. The images that arrived were blurry, grainy, low in resolution by any modern standard. They would be unimpressive compared to what a smartphone camera could produce today, but their content was extraordinary. The far side of the moon looked different. The most immediately striking difference was one of contrast. The near side of the moon, the face we see every night, is divided fairly clearly between two types of terrain. The bright, heavily cratered highlands cover much of the surface, but there are also large, dark regions, the lunar maria, from the Latin word for seas, vast plains of solidified basaltic lava that ancient astronomers mistook for actual bodies of water. These dark plains are what give the near side its familiar patterned appearance, the rough suggestion of a face that cultures around the world have seen in the moon for millennia. The far side had almost none of them. Where the near side has large, dark maria covering perhaps 30% of its visible surface, the far side was almost entirely covered in bright, heavily cratered highlands. The great dark basins were largely absent. The terrain was rougher, more uniformly ancient-looking, more heavily pummeled by billions of years of impacts without the volcanic resurfacing that had smoothed and darkened so much of the near side. It was the same moon, but it looked like a different world. Scientists have spent decades since those first Luna 3 images trying to understand why the two hemispheres are so dramatically different. It remains one of the most actively discussed questions in lunar science, and the answer, or rather, the current best answer, is both elegant and strange. The leading hypothesis involves the early history of the moon's cooling. As the lunar magma ocean slowly solidified billions of years ago, the process may not have been uniform across the entire moon. The near side, perpetually facing the still hot young Earth, may have cooled more slowly than the far side, which faced the cold of open space. This difference in cooling rate could have affected the thickness and composition of the crust that formed on each hemisphere. The far side crust is measurably thicker than the near side crust, in some regions significantly so. A thicker crust is harder for volcanic magma from the interior to punch through. And so when the moon's interior was still warm enough to generate volcanic activity, the eruptions that flooded the Great Impact Basins and created the Dark Maria, the magma was able to reach the surface far more easily on the near side than on the far side. The far side, with its thicker armor of ancient crust, largely kept the magma locked below. The volcanic flooding that transformed the near side never fully reached the other hemisphere. The result is a moon with two faces, not just in the sense of always showing one side to Earth, but in the deeper sense of having two fundamentally different geological histories written across its surface. The far side has continued to reveal surprises. In 2019, a Chinese spacecraft called Chang'e 4 achieved something that had never been done before, a soft landing on the far side of the moon. Because the far side never faces Earth, direct radio communication with a lander there is impossible. China solved this problem by first placing a relay satellite in an orbit above the far side, allowing signals to bounce between the lander and Earth via the satellite intermediary. Chang'e 4 set down in the South Pole Aitken Basin, one of the largest and oldest impact craters in the entire solar system, a depression roughly 2,500 kilometers across and more than 8 kilometers deep. It is so old and so large that it punched through the moon's crust entirely, potentially exposing material from the lunar mantle that would otherwise be buried beyond reach. The data returned by Chang'e 4 and its small rover, Yudu 2, has provided new insights into the composition of the far side's subsurface and added further detail to our understanding of the hemispheric asymmetry. The mission is still ongoing, quietly exploring a landscape that no human eye has directly observed from a surface perspective. The far side of the moon, first glimpsed in blurry Soviet photographs more than 6 decades ago, is still giving up its secrets. There is something philosophically resonant about the moon's hidden hemisphere. We have known the near side for our entire existence as a species. We have mapped it, named its features, watched it through telescopes, visited it in person. It is as familiar as any landscape on Earth, more familiar perhaps since it has not changed in human memory. But the far side remained unknown until within living memory. There are people alive today who were already adults when Luna 3 sent back those first grainy photographs. The far side passed from complete mystery to mapped terrain within a single human lifetime. And still, no person has stood on it. No human eye has looked up from its surface and seen, not the Earth hanging in the sky, but a star-filled darkness where Earth should be, because from the far side, Earth is never visible. It sits permanently below the horizon on the other side of the world. To stand on the far side of the moon would be to stand in a place more isolated than anywhere on Earth, more remote than any ocean floor, any polar ice sheet, any uninhabited island. You would be on a world where the planet that gave birth to the moon is permanently, structurally invisible, where the only connection to home is a radio signal bouncing off a satellite overhead. It is the most profoundly alone place a human being could ever stand. Let that quietness settle around you like darkness. The moon keeps one face toward us always, but on the other side, in the ancient cratered silence, a whole hidden world has been waiting, patient and still, since the beginning. Stand at the edge of the ocean for long enough and you will feel it. Not dramatically, not all at once, but if you plant yourself on a beach or a rocky shore and simply watch over the course of a day, you will notice the water moving in a way that has nothing to do with wind or weather. The sea rises slowly, steadily, climbing the sand, swallowing rocks that were exposed just hours before. And then just as slowly it retreats, pulling back, revealing wet stone and tide pools and the quiet archaeology of the seafloor's edge. This is not random, this is not local. At this same moment, on every coastline, on every continent, on every ocean on Earth, the same slow breathing is happening. The sea rising and falling, twice each day, with a regularity so precise that sailors have predicted it with tables and charts for centuries. And the cause of all of it is a world hanging in space 4,400 kilometers above your head. To understand how the moon moves the oceans, you need to understand something about gravity that is easy to overlook. Gravity does not simply pull, it pulls with different strength at different distances. The closer you are to a gravitating object, the stronger its pull. The farther away you are, the weaker it becomes. This seems obvious, but its consequences, when applied to a large body like Earth, are profound. The moon's gravity does not pull on Earth as if Earth were a single point. It pulls on every part of Earth separately, with slightly different force depending on how far each part is from the moon. The side of Earth facing the moon is pulled more strongly than Earth's center. Earth's center is pulled more strongly than the side facing away from the moon. These differences in gravitational pull across Earth's diameter are called tidal forces. And it is tidal forces, not the moon's gravity in a simple, uniform sense, that are responsible for the tides. Picture what this means for the oceans. On the side of Earth directly facing the moon, the water is pulled toward the moon more strongly than the solid Earth beneath it. The water, being fluid and free to move, responds to this differential pull by bulging outward, rising slightly toward the moon, creating a region of higher sea level on the lunar-facing side of the planet. But something equally interesting happens on the opposite side of Earth, the side facing away from the moon. Here, the solid Earth is pulled toward the moon more strongly than the water on the far side, because the solid Earth is closer to the moon than that far side water. In effect, the Earth is pulled away from the water on its far side, leaving the water behind, and this creates a second bulge of higher sea level on the side of Earth pointing away from the moon. Two tidal bulges, one facing the moon, one facing directly away from it. Earth rotates beneath these bulges, spinning through them, since the bulges are held roughly in place by the moon while Earth turns. As any given point on Earth's surface rotates into one of the bulges, sea level rises. As it rotates out of the bulge, sea level falls. And because Earth passes through two bulges per rotation, most coastal locations experience two high tides and two low tides every 24 hours. The elegance of this mechanism, two bulges, created by differential gravity, producing the rhythmic breathing of the world's oceans, is one of those pieces of physics that rewards slow contemplation. The scale of what the tides move is staggering. In a typical tidal cycle, the volume of water shifted along the world's coastlines is measured in billions of tons. In certain coastal geometries, bays and inlets where the shape of the land amplifies the tidal signal, the effect becomes extraordinary. The Bay of Fundy in eastern Canada experiences tidal ranges of up to 16 meters. 16 meters, the height of a 5-story building, of water rising and falling twice every day, driven by the gravitational influence of a world nearly 400,000 kilometers away. The tides are not merely a coastal curiosity. They are a planetary-scale pumping system, moving enormous quantities of water, redistributing nutrients and sediments, oxygenating coastal ecosystems, and sculpting the physical geography of every shoreline on Earth. Every estuary, every tidal flat, every mangrove forest, every intertidal zone, these entire categories of ecosystem exist because of the moon's gravitational influence. The creatures that inhabit them, the crabs and shorebirds and fish that time their feeding and reproduction to the tidal cycle, are, in a very real sense, living on lunar time. But the moon's influence on Earth's waters goes deeper than the daily rise and fall of the tides. The tidal interaction between Earth and Moon involves a continuous transfer of energy. As Earth rotates and the tidal bulges are dragged around the planet, friction between the moving water and the ocean floor dissipates energy as heat, an almost imperceptible warming of the ocean, spread across its entire floor, but representing a real and ongoing drain on Earth's rotational energy. This is why Earth's days are growing longer, as we touched on in our last section. The tidal breaking of Earth's spin, powered by the moon's gravitational influence, has been slowing our planet's rotation for 4.5 billion years. The energy bled away from Earth's rotation does not disappear. By the conservation of angular momentum, it is transferred to the moon, subtly pushing the moon into a slightly larger orbit, nudging it outward by that now familiar 3.8 centimeters per year. The tides connect Earth and Moon in an ongoing energy exchange. The ocean's daily breathing is not just a passive response to lunar gravity, it is an active part of the mechanism by which the moon slowly retreats and by which Earth's days slowly lengthen. The tides are, in a sense, the physical medium through which Earth and Moon are in constant conversation. There is one more dimension to the moon's influence on Earth's waters that deserves attention, one that operates not on a daily timescale, but on a biological one. Life on Earth's coastlines has had hundreds of millions of years to synchronize itself with the tidal cycle, and that synchronization runs extraordinarily deep. Many marine organisms time their reproduction to specific phases of the tidal and lunar cycle, with a precision that continues to astonish biologists. The grunion, a small fish native to the coast of California, spawns on beaches during the highest tides of the year, precisely timed to full and new moons, laying eggs in the sand just above the waterline so they will incubate safely until the next high tide 2 weeks later carries the hatching larvae back to sea. Coral reefs across the Pacific spawn simultaneously on specific nights following the full moon, releasing eggs and sperm into the water in such vast quantities that the ocean turns milky white, a synchronized reproductive event timed to lunar clockwork. Even human biology carries traces of this ancient connection. The average human menstrual cycle is approximately 29.5 days, almost exactly the length of the lunar month. Whether this is coincidence or a deep evolutionary echo of lunar timing is a question still debated among scientists. But the resonance is there quietly in the most fundamental rhythms of human physiology. The moon does not just move the water, it moves time itself in the biological sense, setting the clock by which countless living things on Earth organize their most essential processes. Listen for a moment to the rhythm of your own breathing. In, out, slow and steady, your body finding its natural pace as wakefulness softens at the edges and rest begins to pull you gently inward. The tides do something similar for the planet. In, out, twice each day. The ocean breathing to a rhythm set by a world of ancient rock in the sky above, a rhythm that has not changed in its fundamental character since the first oceans formed on this planet billions of years ago. Before there was life to hear it, the tide was already rising and falling. Before there were shores to shape, the gravitational conversation between Earth and Moon was already underway. And when the first living things emerged in the shallow coastal waters of the early Earth, they were born into a world already breathing to the moon's rhythm. They learned to breathe with it. And in ways we are only beginning to fully understand, so did we. Let the rhythm carry you now slow and steady like the tide. The moon shapes more than just the water. Next, we will discover how it shaped the very possibility of life itself. There is a question that seems simple on the surface, but the deeper you follow it, the more extraordinary it becomes. Why is Earth alive? Not in the philosophical sense, in the purely physical sense. Our solar system contains 8 planets, dozens of moons, and countless smaller bodies, and as far as we currently know, only one of them is teeming with life. One of them has forests and oceans and birds and fungi and bacteria and human beings who build cities and write music and look up at the night sky and wonder about their place in the universe. What made Earth different? Many answers present themselves: the right distance from the sun, liquid water, a magnetic field shielding the surface from solar radiation, a large planet like Jupiter deflecting some of the most dangerous incoming debris. These are all real factors, genuinely important parts of the story. But there is one factor that does not always make the list, one silent, patient contributor whose role only became clear as our understanding of planetary science deepened. The moon. To appreciate what the moon has done for life on Earth, you first need to understand something about how Earth moves through space. Earth does not sit perfectly upright as it orbits the sun. It tilts. Its rotational axis lanes at an angle of approximately 23.5 degrees relative to the plane of its orbit, and it is this tilt that gives us seasons. When the northern hemisphere leans toward the sun, it receives more direct sunlight and experiences summer. When it leans away, sunlight arrives at a shallower angle and days grow shorter and colder. Winter follows, and then the cycle turns again. This 23.5-degree tilt has been remarkably stable throughout Earth's history. Not perfectly constant, it oscillates very slowly between about 22.1 and 24.5 degrees over a cycle of roughly 41,000 years, a subtle wobble caused by the gravitational influences of the other planets. But this range is narrow, constrained. The tilt varies, but it never strays far from its central value. And that stability, that quiet, persistent steadiness, turns out to be enormously important for the development and maintenance of complex life. Consider what happens to a planet with an unstable axial tilt. Mars offers a sobering example. Mars has no large moon. Its 2 small moons, Phobos and Deimos, are tiny captured asteroids, far too small to exert any meaningful stabilizing gravitational influence on the planet's rotation. Without that stabilization, Mars's axial tilt has wandered dramatically over geological time, ranging from near 0 degrees to perhaps as high as 60 degrees, driven by the gravitational nudges of the other planets, particularly Jupiter. At 0 degrees of tilt, Mars would have no seasons at all. Both poles would receive similar sunlight year-round, and the planet's climate would be locked into a different, less dynamic pattern. At 60 degrees of tilt, the poles would receive more sunlight than the equator during summer, a situation so dramatically different from anything Earth experiences that the climate consequences are difficult to fully model, but certainly extreme. Mars has oscillated between these states over millions of years, its climate swinging through changes far more radical than anything Earth has experienced in its long history. Whatever chances Mars may have had for developing complex, multicellular life, and it may have had some, in its warmer and wetter ancient past, the instability of its axis would have made the long-term maintenance of benign conditions far more difficult. Earth, by contrast, has been held steady. The mechanism by which the moon stabilizes Earth's axial tilt is an extension of the same tidal forces we explored in our last section. The moon's gravitational influence does not only affect Earth's oceans. It acts on the entire planet, on its solid body, its mantle, its moment of inertia. And because the moon is large relative to Earth and relatively close, this gravitational influence is strong enough to act as a kind of gyroscopic anchor, resisting the torques that the other planets try to impose on Earth's rotational axis. Without the moon, computer simulations suggest that Earth's axial tilt could vary chaotically over millions of years, ranging perhaps from near 0 to as high as 85 degrees. At 85 degrees, Earth would be essentially lying on its side, its poles pointing almost directly at the sun for half the year and plunging into complete darkness for the other half. The climate consequences would be catastrophic by any reasonable biological standard. With the moon, Earth's tilt is kept within that narrow, stable range. The seasons cycle predictably. The climate zones, tropical, temperate, polar, remain recognizable over geological time. The conditions that life requires, not just warmth or water, but consistency, predictability, a world that does not swing between extremes faster than evolution can adapt, are maintained. The moon is not just a companion, it is a stabilizer, a governor, a gravitational hand on Earth's shoulder, steadying the planet through billions of years of subtle external pressures. The implications for life are deep. Complex multicellular life, animals, plants, fungi, everything beyond single-celled organisms, requires time. Not just millions of years, but hundreds of millions, billions. The evolutionary processes that produced creatures capable of building cities and studying the moon took nearly 4 billion years to run from the first primitive cells to their current endpoint. That process requires not just the right conditions, but the right conditions maintained over an almost incomprehensible span of time. A planet whose axial tilt wanders chaotically would periodically experience climate shifts severe enough to drive most complex life to extinction, not the gradual, punctuated extinctions that have occurred on Earth and from which life has repeatedly recovered, but something more fundamental. A resetting of conditions so extreme that the slow accumulation of biological complexity would be interrupted again and again, never reaching the level of organization needed for intelligence, civilization, or curiosity. Earth has had extinctions, terrible ones. The asteroid impact 66 million years ago that ended the reign of the non-avian dinosaurs was catastrophic by any measure. But even that event, even that dramatic reshaping of life on Earth, was recoverable. The planet's fundamental climate stability, maintained in part by the moon's gravitational steadiness, meant that enough biodiversity survived to fuel a new phase of evolutionary radiation. Life bounced back, life always bounced back, because the conditions for life, stable seasons, predictable climate zones, consistent temperatures across geological time, were always waiting on the other side of the disaster. That consistency is the moon's gift. There is another contribution the moon made to life's early development that operates on a different time scale, not millions of years, but daily. The tides we explored in our last section did more than sculpt coastlines and set biological clocks. In the early Earth, when the moon was much closer and tidal forces were much stronger, the tides reached far inland, sweeping across vast shallow coastal regions, alternately flooding and exposing enormous stretches of land in shallow water. These tidal zones, repeatedly wetted and dried, enriched with minerals washed from the land and organic molecules concentrated by evaporation, may have been among the most chemically productive environments on the early Earth. Some scientists believe that the rhythmic wetting and drying of tidal pools could have played a role in the chemistry that led to the first self-replicating molecules, the earliest precursors to life itself. The moon, in this view, was not merely a stabilizer for existing life. It may have helped create the conditions in which life first ignited. Step outside on a clear night and look up. That pale disk above you has been doing this work for longer than the oldest rock on Earth's surface, longer than the oldest fossil, longer than the oldest ocean. Since before the first living cell divided for the first time in some warm, shallow pool of early Earth, the moon has been turning in its orbit, steadying the planet, pulling the tides, holding the axial tilt within its narrow, livable range. It asked for nothing in return, it made no sound, it simply orbited, and in orbiting, it gave Earth something that may be rarer in the universe than we like to imagine: stability, predictability, the slow, patient consistency that life requires to grow from simplicity into complexity, from a single cell into a civilization capable of understanding what the moon has done for it. We have spent our entire existence as a species beneath a sky that the moon was quietly managing. Every breath of every living thing that has ever existed on this planet has been drawn in a world the moon helped make possible. That is not poetry. That is planetary science. Breathe slowly now. The moon has been holding the world steady for billions of years, and tonight, as you rest, it is still doing exactly that. Imagine tonight is the last night. Not the last night in any human sense, not the end of civilization or the dying of the sun or any catastrophe born of human making. Something quieter than that, something that happens not with fire or noise, but with a simple, impossible subtraction. Imagine that when the sun rises tomorrow, the moon is gone. Not destroyed, not exploded into a dramatic debris field spreading across the sky. Simply absent, removed as cleanly as a word erased from a sentence. The orbit empty, the night sky unbroken by any companion world, just stars and darkness and a planet suddenly, completely alone. What happens next is not a matter of speculation or science fiction. It is physics, and physics, in this case, tells a story of slow, creeping catastrophe, not sudden and violent, but relentless and irreversible. A story of a world gradually, inevitably becoming unrecognizable. The first thing you would notice in the days and weeks following the moon's disappearance is the ocean. The tides would not stop immediately. The sun also exerts a tidal influence on Earth, smaller than the moon's, but real and measurable, contributing roughly 40% of the total tidal force that drives the world's oceans. Solar tides would continue. But the great twice-daily breathing of the sea, the dramatic rise and fall that has shaped every coastline on Earth and set the biological clock of countless species, would diminish dramatically. The tidal range in most locations would drop to perhaps a third of what it is today. The Bay of Fundy, where tides currently reach 16 meters, might see ranges of 5 or 6 meters. Coastal ecosystems built around the rhythm of tidal flooding and exposure would be disrupted. Species whose reproduction, feeding, and migration patterns are synchronized to the lunar tidal cycle would find that synchronization suddenly meaningless. Their biological clocks ticking to a rhythm the ocean no longer follows. The intertidal zone, that rich, productive band of coastline between high and low water marks, would shrink. The estuaries and tidal flats that serve as nurseries for enormous proportions of marine life would contract. The consequences would ripple through marine food webs in ways that are difficult to fully model, but certainly significant. The ocean without the moon would still move, but it would breathe more shallowly, and the living world built around its deeper breathing would feel the change immediately. But the ocean's altered tides are only the beginning, and they are, in the long run, among the least of Earth's problems. The deeper consequence of losing the moon would take longer to manifest, years, decades, centuries, but it would be far more fundamental. Without the moon's gravitational steadying influence, Earth's axial tilt would begin to drift. Not quickly, not noticeably from year to year, or even century to century. The drift would be subtle at first, a degree here, a fraction of a degree there, driven by the gravitational perturbations of Jupiter, Saturn, and the other planets, no longer counterbalanced by the moon's stabilizing torque. But the drift would accelerate and compound, and over tens of thousands of years, Earth's tilt could wander far outside the narrow range it has maintained throughout the history of complex life. Computer simulations of a moon-free Earth suggest tilt values ranging from near zero to as high as 85 degrees, a chaotic wandering across the full spectrum of possible orientations. The climate consequences of this wandering would be severe, and they would escalate as the tilt moved further from its current value. At a tilt of near 0 degrees, Earth would lose its seasons almost entirely. The tropics would remain hot. The poles would receive even less sunlight than they do today, cooling dramatically. The great seasonal cycles that drive weather patterns, ocean circulation, and biological productivity across the planet would slow and quiet. The world would become more static, more extreme in its latitudinal temperature differences, and less hospitable to the diversity of life forms that depend on seasonal variation for their reproductive cycles, their migrations, and their energy budgets. At a tilt of 45 degrees or more, the seasons would become something unrecognizable. Summer in the high latitudes would bring months of near-continuous sunlight intense enough to bake the soil and evaporate surface water at catastrophic rates. Winter would bring months of absolute darkness and temperatures dropping far below anything currently experienced outside polar regions. The temperature swings between seasons at mid-latitudes, where most of Earth's human population currently lives, would become so extreme as to make year-round habitation of those regions essentially impossible for most forms of complex life. And the tilt would not stay at any one value, it would keep moving, oscillating chaotically, spending time at some values and then swinging to others, giving life no stable target to adapt to, no consistent set of conditions to build upon over the millions of years that evolutionary adaptation requires. There is a subtler consequence of losing the moon that deserves its own quiet moment of consideration. Earth's rotation would no longer be slowing. Right now, the moon's tidal braking is gently, continuously decelerating Earth's spin. Without the moon, that braking force vanishes. Earth's rotation would remain at whatever speed it had reached by the time the moon disappeared, our current 24-hour day, but it would no longer be slowing down. More significantly, other forces, smaller tidal interactions with the sun, the subtle effects of atmospheric dynamics, would still act on Earth's rotation. But without the dominant lunar braking to set the pace, the behavior of Earth's spin over geological time would change in ways that are difficult to fully predict. The length of the day would become a more chaotic variable, no longer evolving along the smooth, predictable trajectory set by lunar tidal friction. For life, the length of the day matters more than it might seem. The metabolic rhythms of nearly every living thing on Earth are organized around the 24-hour light-dark cycle, what biologists call the circadian rhythm. Plants, animals, fungi, bacteria, all carry internal clocks calibrated to the current day length. A world in which day length drifted significantly over geological time would require continuous biological adaptation just to keep pace with the shifting rhythm of light and darkness. It is another variable that life, without the moon, would have to cope with on top of everything else. Pull all of these threads together and a picture emerges, not of a single catastrophe, but of a slow accumulation of instabilities, each compounding the others, pushing Earth progressively further from the conditions that allowed complex life to develop and flourish. The shrinking tides disrupting coastal ecosystems, the wandering axial tilt destabilizing climate zones, the chaotic seasons preventing the long-term consistency that evolutionary complexity requires, the changing day length adding yet another variable to an already unstable system. None of these changes would necessarily end all life on Earth. Life is extraordinarily resilient. Microorganisms have survived every mass extinction in Earth's history and would almost certainly survive the loss of the moon as well. But complex life, multicellular animals, ecosystems of interlocking species, the kind of biological richness that took 4 billion years to build, is far more fragile. It requires not just tolerable conditions, but consistent ones, maintained over timescales that dwarf the entire history of human civilization. A moon-free Earth might still harbor life, but it is far less likely to harbor life like us. There is something quietly humbling about sitting with this thought on an ordinary night. The moon above you right now is not simply beautiful, it is functional, it is working. At this moment, its gravity is pulling gently on Earth's oceans, maintaining the tidal rhythms that coastal ecosystems depend on. Its gravitational influence is pushing back against the slow perturbations that Jupiter and Saturn are exerting on Earth's rotational axis, keeping the planet's tilt within the narrow range that makes stable seasons possible. Its very presence in orbit is part of the architecture of conditions that allowed you to exist. You did not earn this, no living thing did. It is simply the arrangement of the solar system we happen to inhabit, one where a collision 4.5 billion years ago produced a debris disk that coalesced into a moon large enough, and at a distance close enough, to do all of this work quietly and continuously for the entire history of complex life on Earth. Other planets may not be so fortunate. Other worlds orbiting other stars may spin and tilt in chaotic isolation, their oceans calmer, their axes wandering, their seasons swinging between extremes that life can never quite get ahead of. We got lucky. And the measure of our luck hangs in the sky every night, familiar and quiet, doing its work without asking to be noticed. Let that gratitude settle softly into rest. The moon is there, steady, patient, faithful. And in our next passage, we turn to the moment when humanity first dared to reach for it. There are moments in history that do not feel like history while they are happening. They feel like desperation, like national pride stretched to its breaking point, like engineers working through the night on calculations that could mean the difference between triumph and catastrophe. Like astronauts lying on their backs inside a capsule barely larger than a closet, feeling the vibration of a rocket beneath them that carries enough fuel to level a small city, waiting for a countdown to reach zero. Only later, sometimes decades later, do those moments settle into what they actually were, turning points, thresholds, the kind of before and after lines that divide human history into two distinct chapters. July 20th, 1969 is one of those lines. But to understand what that date meant, to feel its full weight, you have to go back to the world that made it necessary. Back to a time when the moon was not a destination but a symbol, and symbols in the middle of the 20th century had become weapons. The story of the space race does not begin in space. It begins on the ground in the rubble of the Second World War, in a competition between two superpowers for the minds, the technology, and the allegiance of a watching world. The United States and the Soviet Union emerged from that war as the dominant forces on Earth, and almost immediately, they began competing for dominance everywhere else. Space was not initially the arena either side had chosen. But on October 4th, 1957, the Soviet Union launched a small metal sphere into orbit around Earth, and the arena changed overnight. Sputnik, 83 kilograms of polished aluminum, carrying nothing but a radio transmitter that beeped a simple signal as it crossed the sky. It did not carry weapons. It did not carry instruments of any scientific sophistication. It simply orbited, beeping, visible to the naked eye as a moving point of light crossing the night sky over American cities. The psychological impact was enormous. If the Soviets could put a satellite into orbit, they could put a warhead there too. The sky, which Americans had always thought of as a barrier, suddenly felt like a highway, and the Soviet Union was already on it. The race began in earnest. What followed was one of the most extraordinary sustained mobilizations of human talent and resources in history. Both superpowers poured money, engineering genius, and national prestige into their space programs with an urgency that peacetime economies rarely generate. The Soviets accumulated early victories. They launched the first animal into orbit, a dog named Laika, in 1957. They sent the first human to space, Yuri Gagarin, on April 12, 1961, completing one orbit of Earth in 108 minutes and returning as the most famous person on the planet. Each Soviet achievement landed in Washington like a strategic defeat. The pressure on American engineers, scientists, and politicians was intense, not just to catch up, but to find something the Soviets had not yet done. Something so ambitious, so demanding, so publicly visible that achieving it first would redefine the entire competition. On May 25, 1961, 6 weeks after Gagarin's flight, at a moment when American spaceflight had achieved exactly 15 minutes of suborbital travel, President John F. Kennedy stood before Congress and made an announcement that startled even the engineers who would have to fulfill it. The United States, he declared, would land a human being on the moon and return them safely to Earth before the end of the decade. The engineers heard this and understood immediately what it meant. It meant solving problems that did not yet have solutions, building rockets that did not yet exist, developing navigation techniques, life support systems, spacesuits, landing vehicles, and re-entry procedures from scratch, simultaneously under pressure, in less than 9 years. At the moment Kennedy made his speech, NASA had not yet put an astronaut into orbit. The rocket that would eventually carry humans to the moon had not been designed. The technique that would actually be used to land on the moon, sending a separate, smaller spacecraft down to the surface while a larger vehicle waited in lunar orbit, had not been decided upon. Everything was still a question. What followed was the Apollo program, arguably the most complex engineering project in human history up to that point. At its peak, more than 400,000 people were working on it. Engineers, mathematicians, machinists, seamstresses who hand-stitched the layers of space suits, programmers who wrote navigation software in an era before calculators were common. An entire industrial ecosystem assembled around a single impossible goal. The path to the moon was not smooth. On January 27, 1967, a fire broke out inside an Apollo command module during a ground test at Cape Kennedy. 3 astronauts, Gus Grissom, Ed White, and Roger Chaffee, were killed. The program was grounded for nearly 2 years while engineers redesigned the spacecraft, replacing the pure oxygen atmosphere that had fed the fire, adding escape hatches, replacing hundreds of components that had been built to meet schedules rather than to meet the demands of space. The Soviet program suffered its own tragedies. Cosmonaut Vladimir Komarov was killed in 1967 when his Soyuz spacecraft's parachute failed on re-entry. Sergei Korolev, the brilliant chief designer whose vision had driven Soviet space achievements, had died the previous year during surgery. The Soviet moon program, beset by technical failures and internal conflicts, never recovered its momentum. By 1968, the race was narrowing, and NASA, rebuilt and recalibrated after the fire, was ready to attempt something that had never been done in the history of our species. Apollo 8 in December 1968 carried 3 astronauts out of Earth orbit for the first time, not to land on the moon, but to circle it. To enter lunar orbit, see the far side with human eyes, and return home safely. On Christmas Eve, as the spacecraft came around the near side of the moon and saw the Earth rising above the lunar horizon, astronaut William Anders took a photograph that would become one of the most reproduced images in history. Earthrise, a small, blue, heartbreakingly fragile sphere, suspended in absolute blackness above a gray and desolate lunar surface. It did not show the moon, not really. It showed Earth, our home, our pale blue island in an ocean of nothing, from a perspective no human had ever had before. And something shifted in the collective human consciousness when that image circulated around the world. Something about the smallness of home, the loneliness of space, the preciousness of the blue world hanging there in the dark. Apollo 8 had gone to the moon and come back with a picture of Earth. 6 months later, in July 1969, Apollo 11 sat on the launch pad at Cape Kennedy. 3 astronauts, Neil Armstrong, Buzz Aldrin, and Michael Collins, had been living with this mission for years, training in simulators, studying lunar maps, learning procedures so thoroughly that they could execute them from memory in conditions of stress and disorientation. They knew the risks. The systems were as reliable as human engineering could make them in 1969, which meant they were not entirely reliable. The landing itself would require a degree of manual piloting that no simulation could fully prepare for, setting down on a surface no human had ever touched, in a vehicle that had never been tested in actual lunar conditions, with no possibility of rescue if anything went wrong. On July 16th, the Saturn V rocket ignited beneath them, generating more thrust than 30 Boeing 747 engines simultaneously, and lifted slowly, then faster, then impossibly fast, into the blue Florida sky. The moon was 3 days away. What they found when they got there, what the moon actually turned out to be, up close, in person, under their boots, was stranger and more scientifically rich than almost anyone had fully anticipated. But that is the story waiting for us in the next passage. For now, rest in the magnitude of the journey itself. 400,000 kilometers, 8 days. 3 human beings in a spacecraft smaller than most modern bathrooms, crossing the void between worlds for the first time in the history of life on Earth. They went because 2 nations were competing. They went because a president made a promise. They went because engineers refused to say impossible. But they also went because the moon had been hanging in the sky above human beings for our entire existence, familiar and unreachable, beautiful and mysterious, and something in us simply could not leave it that way. Let that quiet courage carry you into sleep. The journey has been made, and what they found when they arrived will change everything we thought we knew. They had trained for every contingency they could imagine. Thousands of hours in simulators, geology field trips to volcanic landscapes in Iceland and Hawaii, chosen because their ancient lava fields vaguely resembled what scientists expected the lunar surface to look like. Briefings from geologists, physicists, engineers. Conversations about what the moon might feel like underfoot, what the light might look like without an atmosphere to soften it, what it would mean to stand on another world and look back at the one you came from. And still, nothing quite prepared them for the reality. When Neil Armstrong descended the ladder of the lunar module Eagle on July 20th, 1969, and placed his boot on the surface of the moon for the first time, what he stepped into was not the solid, rocky ground most people had imagined. The surface yielded slightly, a fine, powdery layer of ground-up rock, the result of billions of years of micrometeorite impacts slowly pulverizing the lunar crust into something closer to talcum powder than gravel. His boot sank perhaps a centimeter or 2, leaving a crisp, perfect impression in the dust. That footprint is still there, exactly as he left it, unchanged. And in that single detail, a footprint preserved in the stillness of an airless world, the moon began immediately to reveal how profoundly different it was from anything human beings had ever encountered. The light was the first thing that struck the astronauts as genuinely alien. On Earth, even on the clearest day, the atmosphere scatters sunlight in all directions, filling shadows with diffuse illumination, softening contrasts, wrapping the world in a pervasive ambient glow. The sky is blue because of this scattering. Shadows are never truly black because scattered light always finds its way into them. On the moon there is no atmosphere, none, not a trace. Sunlight arrives unfiltered and unscattered, striking the surface with a harshness that photographs struggle to capture. Directly illuminated surfaces are brilliantly, almost painfully bright. Shadows are absolute, not dim, not dark gray, but black, completely black. A rock half in sunlight and half in shadow appears to be 2 completely different objects. The contrast between light and dark on the lunar surface is unlike anything found in nature on Earth. And the sky above, the sky that astronauts could see beyond their visors, was not blue. It was not any color at all. It was black, the pure uncompromising black of space, even with the sun blazing in it. Stars were invisible, washed out by the brightness of the sunlit surface, but the darkness between sun and horizon was absolute. It was, by every account, beautiful and deeply, fundamentally strange. The rocks told a story that scientists had not fully expected. When the Apollo astronauts collected samples, chipping them from outcrops, scooping them from the surface, drilling cores from below the dust layer, and returned them to Earth for analysis, the scientific community had one of its most productive periods of lunar research in history. The samples were distributed to laboratories around the world, analyzed by hundreds of scientists using every technique available. And what emerged from that analysis was a portrait of the moon, far more complex and scientifically rich than most pre-Apollo models had predicted. The dark basaltic rocks from the lunar maria, the flat plains that had been flooded by ancient volcanic eruptions, were extraordinarily old. Some dated to more than 3 billion years ago, others to nearly 3.9 billion. These were rocks that had formed, cooled, and sat essentially undisturbed on the lunar surface for longer than the oldest surviving rocks on Earth. They were time capsules, chemical records of conditions in the early solar system that Earth's own geological activity had long since erased. The highland rocks, the ancient anorthosite crust we explored in an earlier section, were older still. Some samples returned ages exceeding 4 billion years, placing them among the most ancient solid materials ever studied by human science. Geologists who had spent careers studying Earth, where rocks are constantly recycled by plate tectonics, weathered by wind and water, transformed by heat and pressure, found themselves holding material from a world that had simply stopped. A geological clock that had wound down billions of years ago and preserved its final moment in extraordinary detail. One of the most significant scientific surprises was what the rocks revealed about the Moon's relationship to Earth. The isotopic signatures, those precise atomic fingerprints we discussed when examining the giant impact hypothesis, confirmed with striking clarity that Earth and Moon share a common origin. The oxygen isotope ratios in lunar samples matched Earth's mantle rocks more closely than any other known body in the solar system. Titanium isotopes told the same story. Silicon isotopes agreed. The Moon is made of Earth, not entirely and not simply. The giant impact mixed and modified and partially differentiated the material that became the Moon, but the fundamental connection is written unmistakably in the chemistry of the rocks. When Armstrong and Aldrin picked up pieces of the lunar surface and placed them carefully in sample bags, they were, in a very real sense, picking up pieces of the early Earth, material that had been blasted into orbit by the collision with Theia, gathered into a new world, and preserved in pristine isolation for 4.5 billion years. They were bringing home something that had been away for a very long time. The Moon also surprised scientists with what it revealed about its own interior. Each Apollo landing site was equipped with seismometers, instruments designed to detect vibrations traveling through the lunar body, the equivalent of earthquake detectors on the Moon, and what those instruments recorded was unexpected. Moonquakes exist. The Moon is not entirely geologically dead. It experiences small seismic events caused by tidal stresses from Earth's gravity, by the dramatic temperature swings between lunar day and night, and occasionally by meteorite impacts. These moonquakes are generally small by Earth standards, but they revealed something striking about the Moon's interior structure. When a meteorite struck the lunar surface near one of the seismometer arrays, or when a spent rocket stage was deliberately crashed into the Moon to create a known seismic event, scientists listened to how the vibrations traveled through the Moon's body. The result, in the words of one scientist, was that the Moon rang like a bell, vibrations traveling through the deep interior for an extraordinarily long time before dying away, suggesting a cold, rigid, dry interior very different from Earth's hot, partially molten mantle. The Moon's deep interior turned out to be ancient, cold, and largely frozen in its geological history, a contrast to Earth's dynamic, heat-driven interior that told scientists a great deal about the different evolutionary paths two worlds born from the same collision had taken. 6 Apollo missions landed successfully on the Moon between 1969 and 1972. 12 human beings walked on its surface. They drove a battery-powered rover across the lunar landscape, descended into craters, climbed the slopes of ancient hills, collected samples from a remarkable variety of geological contexts. Each mission returned with not just rocks, but data, seismic readings, heat flow measurements, laser-ranging reflectors that are still in use today, photographs of landscapes no human eye had seen before and no human foot had touched. Taken together, the Apollo program transformed our understanding of the Moon from a mysterious light in the sky to a known world, one with a geological history, a chemical identity, a structural complexity that rivaled anything found on Earth. And yet, even after all of it, the Moon kept secrets. One of them, perhaps the most practically significant, had to do with something so simple, so fundamental, that its absence had long been taken for granted. Water. For decades after Apollo, the scientific consensus was clear. The Moon was bone dry. completely, utterly, definitively devoid of water in any form. The samples confirmed it, the models supported it. The moon, baked by solar radiation on its day side and frozen in shadow on its night side, with no atmosphere to trap or transport moisture, simply could not hold water. That consensus would turn out to be wrong. But the discovery of lunar water, one of the most consequential findings in planetary science of recent decades, belongs to a later chapter of our story. For now, let the image of those 12 human beings rest gently in your mind. 12 people who walked on another world, who picked up its ancient rocks and carried them home, who left their footprints in dust that will outlast every building, every city, every civilization humanity will ever build. They went to explore, they went to compete. They went because the moon had called to human beings since the first night our ancestors looked up and wondered. And they came back changed, every one of them, by what it felt like to stand on the surface of another world and look up at the earth hanging small and blue and impossibly beautiful in the black sky above them. Let that image carry you gently into stillness. The moon was explored and its secrets began to open, and next, we will discover what those 12 pairs of footprints left behind and how long they will last. Think about the most permanent thing you have ever made. Perhaps a photograph printed and framed, perhaps a letter written in ink on good paper, folded and kept in a drawer. Perhaps a building you helped construct or a tree you planted in a yard that still stands. These things feel lasting. They feel like they will outlast you, and some of them will, for a generation or two, or perhaps a century if they are lucky and well cared for. Now consider this. Somewhere on the surface of the moon, in the Sea of Tranquility, there is a shallow impression in fine gray dust. It is approximately 30 centimeters long and perhaps 12 centimeters wide. Its edges are crisp, its tread pattern is perfectly preserved. Every ridge and groove of the boot that made it is still exactly where it was on the evening of July 20th, 1969, when a human foot pressed down into the lunar regolith for the first time in history. That footprint will still be there in 1,000,000 years. It will still be there in 10 million years. Barring a direct meteorite strike, an event of low but non-zero probability over such timescales, it will remain recognizable, largely unchanged, for hundreds of millions of years. Long after every trace of human civilization on Earth has been erased by time and geology and the slow rewriting of the planet's surface. Long after the languages we speak have become as incomprehensible as the calls of extinct birds. Long after the mountains we live beneath have been worn flat by erosion and replaced by new ones pushed up by plate tectonics. The footprint will still be there. To understand why, you need to understand what the moon lacks. On Earth, preservation is the exception, destruction is the rule. The forces arrayed against permanence on our planet are overwhelming in their variety and persistence. Wind carries particles that sandblast rock faces smooth over millennia. Rain dissolves minerals and carries them to the sea. Rivers cut canyons and fill them again with sediment. Plants send roots into cracks, splitting stone. Freeze and thaw cycles fracture even the hardest surfaces. Plate tectonics subducts ocean floors and recycles continental crust back into the mantle. And over all of it, the atmosphere wraps Earth in a chemically active blanket of oxygen and water vapor that reacts with nearly every surface it touches, slowly oxidizing, hydrating, and chemically transforming everything it contacts. The moon has none of this. No atmosphere, no wind, no rain, no rivers, no ice that freezes and thaws, no plate tectonics, no oxygen to oxidize exposed surfaces, no water to dissolve or transport minerals, no biological activity of any kind to break down, consume, or transform what sits on the surface. The moon's surface environment is, from the perspective of preservation, almost perfect. Objects placed there, or impressions made there, experience essentially no forces capable of erasing them on human timescales. On geological timescales, the primary agents of change are micrometeorite impacts and the slow gardening effect of cosmic rays and solar wind particles gradually churning the uppermost layer of regolith. But these processes are extraordinarily slow. The footprints are safe for time periods that dwarf the entire history of complex life on Earth. The Apollo astronauts left more than footprints. At each of the 6 landing sites, the descent stage of the lunar module remains on the surface, the lower half of the spacecraft that carried astronauts down from lunar orbit, which stayed behind as the ascent stage fired its engine and carried the crew back up to rendezvous with the command module. These descent stages are still there. 6 of them scattered across the near side of the moon, their gold and silver thermal insulation slowly degrading under ultraviolet radiation and cosmic ray bombardment, but their fundamental structures intact. Nearby at most sites, American flags still stand, or stood, until the exhaust from the ascending lunar modules blew them over. The flags themselves have almost certainly been bleached white by decades of unfiltered solar ultraviolet radiation. The fabric that was manufactured in the late 1960s was not designed to withstand half a century of direct exposure to space. But the poles may still be there, and the shape of the fallen or standing flags preserved in the stillness of the lunar environment. Scientific instruments were left at several sites: seismometers, laser ranging reflectors, heat flow probes. Some of these instruments operated for years after the astronauts left, transmitting data back to Earth before their power supplies failed. The laser ranging reflectors require no power and are still in active use today, more than 50 years after they were placed, bounced by laser pulses from observatories on Earth to measure the moon's distance with millimeter precision. Human artifacts frozen in the moment of their placement, waiting in the silence. There is something about the lunar environment that makes this preservation feel almost intentional, as if the moon were keeping something for us, holding our history in trust. On Earth, we build museums and archives and libraries to preserve the past. We laminate documents, control humidity, filter light, regulate temperature, employ conservators whose entire careers are devoted to slowing the inevitable decay of the things we want to remember. And still, we lose things. The Library of Alexandria burned, paintings crack and fade. Stone inscriptions weather into illegibility. The past is always escaping us, molecule by molecule, century by century. The moon preserves without effort, without intention, simply by being what it is: airless, dry, geologically quiet, removed from all the forces that make Earth such a difficult place to leave a lasting mark. The footprints in the Sea of Tranquility will outlast the pyramids of Giza by a factor of thousands. They will outlast the mountains currently rising in the Himalayas. They will still be identifiable as human footprints long after the sun has brightened enough to make Earth's surface significantly hotter than it is today. They are, in the most literal sense, the most permanent marks our species has ever made. The lunar regolith itself, that fine, powdery layer of ground-up rock that the astronauts walked through and complained about and brought home in their sample bags, is a remarkable substance in its own right. It is not like soil, it is not like sand, it is not like any Earth material that closely resembles it in appearance. Lunar regolith is the product of billions of years of micrometeorite bombardment, cosmic ray exposure, and solar wind implantation. A complex mixture of rock fragments, glass beads formed by the heat of ancient impacts, and particles so fine they behave almost like a fluid, clinging to everything they touch with an electrostatic tenacity that drove Apollo engineers to distraction. The astronauts found it everywhere. It coated their suits within minutes of stepping onto the surface. It worked its way into every joint and seal and mechanism. It scratched visors. It smelled when carried inside the lunar module on suits and equipment, like something the astronauts described as gunpowder or spent fireworks, a distinctive scent from the chemical reactions occurring as freshly exposed regolith encountered the relatively humid air of the cabin for the first time. This powdery, clinging, chemically reactive material is also what makes the footprint so perfect, fine enough to take a crisp impression, stable enough to hold it, undisturbed by any force capable of erasing it. From lunar orbit, the Apollo landing sites are visible, not the equipment or the flags, which are far too small, but the disturbances in the regolith. The Lunar Reconnaissance Orbiter, a NASA spacecraft that has been imaging the moon from low orbit since 2009, has photographed all 6 Apollo landing sites with sufficient resolution to see the darker disturbed soil where astronauts walked, the tracks left by the lunar rovers, even the shadows of the descent stage equipment. From a camera in lunar orbit, more than 50 years later, you can see where 12 human beings walked. The surface remembers. There is a particular kind of peace in knowing this. We live in a world where things fade, where the things we make and the marks we leave are subject to the patient, relentless erosion of time, where even the most carefully preserved records eventually become illegible and the most enduring monuments eventually crumble. There is beauty in this impermanence. It is part of what makes living things precious, what gives moments their weight. But there is also something quietly comforting about the thought that somewhere, on a world where time moves differently, where nothing corrodes, nothing weathers, nothing shifts, 12 pairs of human footprints are waiting in the dust. Patient, permanent, faithful. A record of the first time our species crossed the distance between worlds and stood, however briefly, on another one. They will still be there long after everything else we have ever built has returned to the earth from which it came. Rest in that permanence. The footprints wait in the stillness of the lunar surface, and next we turn to one of the moon's greatest secrets, hidden in plain sight for decades. For decades, the answer seemed settled. Not tentative, not provisional. Not the kind of scientific consensus that carries an asterisk or a footnote suggesting the matter might be revisited. The moon was dry, completely, irreversibly, bone dry. This was not a guess or an assumption. It was a conclusion drawn from the most direct evidence available. Rocks collected by human hands from the lunar surface, carried back across nearly 400,000 kilometers of space, analyzed by some of the finest laboratories on Earth. Those rocks contained no water, none, not a trace of hydration in their mineral structures, not a hint of the chemical signatures that water leaves behind in rock when it passes through. The Apollo samples were, by the standards of geological analysis, extraordinarily dry, drier than the driest desert rock on Earth, drier than anything most geologists had ever handled. The conclusion seemed inescapable. The moon, baked by unfiltered solar radiation during its 2-week-long days and exposed to the hard vacuum of space across its entire surface, simply could not hold water in any form. Whatever water might have existed early in its history had long since been lost, evaporated, dissociated by solar ultraviolet radiation into hydrogen and oxygen atoms, and stripped away into space by the solar wind. The moon was dry, case closed. Except it was not. The first crack in the consensus came not from a dramatic discovery, but from a question. A quiet, persistent, nagging question that a handful of scientists kept returning to even as the broader community moved on. The question was about shadows. The moon's axial tilt is extremely small, only about 1.5 degrees compared to Earth's 23.5 degrees. This means that the moon essentially does not have seasons in any meaningful sense. The sun, as seen from the lunar surface, never rises very high above the horizon near the poles. It skims along at a low angle, casting long shadows across the terrain. And near the poles, in the floors of certain deep craters whose rims are high enough and whose floors are deep enough, the sun never rises at all. The geometry of the lunar poles creates regions where sunlight has not touched the surface in billions of years, perhaps ever. These permanently shadowed regions sit in a darkness more complete than any on Earth, with no atmosphere to scatter light around corners, no diffuse illumination to creep into the shadows, no warmth radiating from nearby sunlit ground sufficient to raise temperatures significantly. The floors of these polar craters are among the coldest places in the solar system. Temperatures in the deepest, permanently shadowed craters near the lunar poles dropped to around -250 degrees Celsius, colder than the surface of Pluto. And at those temperatures, something interesting happens to water ice. It does not sublimate, it does not evaporate, it simply stays, locked in place by cold so extreme that even in the vacuum of space, water molecules lack the energy to escape. A permanently shadowed crater near the lunar poles, scientists began to realize, was theoretically a perfect cold trap, a place where water ice delivered by comets or asteroids billions of years ago could have accumulated and survived, undisturbed for geological timescales. The theory was elegant, but theory is not evidence. The search for evidence began in earnest in the 1990s, as a new generation of spacecraft began exploring the moon with instruments far more sophisticated than anything available during the Apollo era. In 1994, a joint NASA Department of Defense mission called Clementine entered lunar orbit carrying a radar instrument. Its primary mission was to test spacecraft technologies, but scientists seized the opportunity to bounce radar signals off the lunar surface, including into the permanently shadowed regions near the poles. The radar returns from some polar areas showed characteristics that could be consistent with ice deposits buried beneath the surface. Could be, might be, possibly. The data was intriguing but not conclusive. Radar signals can be affected by many factors: the angle and roughness of the surface, the composition of the rock, the presence of other minerals with radar-reflective properties. Ice was one possible explanation, not the only one. In 1998, the Lunar Prospector spacecraft arrived in lunar orbit carrying a neutron spectrometer, an instrument designed to detect hydrogen by measuring the way it slows down neutrons produced by cosmic ray bombardment of the lunar surface. Hydrogen, the key component of water, leaves a measurable signature in the neutron flux above the surface. Lunar Prospector found it, concentrated near both poles, consistent with hydrogen-bearing material, possibly water ice, buried within the top meter of the lunar regolith. Still not definitive, hydrogen can exist in forms other than water. The instrument could not distinguish between water ice and, say, hydrogen implanted directly by the solar wind. But the signal was there, in exactly the places the cold trap theory predicted. The case for lunar water was building, slowly, carefully, one indirect measurement at a time. Then came the experiment that removed all remaining doubt. On October 9, 2009, NASA executed one of the more unusual missions in space exploration history. The Lunar Crater Observation and Sensing Satellite, LCROSS, was designed around a deliberately destructive purpose. A spent rocket upper stage, weighing approximately 2.5 tons, was steered into a controlled impact with the floor of Cabeus crater near the moon's south pole, a permanently shadowed region that had not seen sunlight in billions of years. The impact was calculated to excavate a column of material from the subsurface and blast it upward into sunlight, where a following spacecraft could fly through the debris plume and analyze it with spectrometers before itself crashing into the surface. The rocket stage hit the crater floor at approximately 2.5 kilometers per second, releasing energy equivalent to roughly 2 tons of TNT. The impact excavated a crater approximately 20 meters wide and raised a plume of material that rose above the crater rim into sunlight. The LCROSS spacecraft flew through that plume in the minutes following the impact, its instruments collecting data at high speed before it, too, impacted the surface. When scientists analyzed the spectrometer data, they found what they had been looking for. Water, unambiguous, unmistakable water, detected in the vapor and ice particles thrown up by the impact. The signal was clear. The spectral signatures were definitive. The permanently shadowed floor of Cabeus crater contained water ice. The moon was not dry. It had never been entirely dry. The Apollo rocks, it turned out, had not been wrong. The The samples collected from the equatorial and mid-latitude landing sites, regions bathed in solar radiation, far from the permanently shadowed polar cold traps, genuinely were extraordinarily dry. Water cannot survive in those sun-exposed locations. But the poles are different. The poles have places where sunlight has never reached. And in those places, over billions of years, water delivered by comets and asteroids, and even by the solar wind itself, had accumulated, molecule by molecule, into deposits that had waited in the cold and dark for longer than complex life has existed on Earth. The moon had been keeping a secret, not through any deception, but simply because we had only looked in the places we could reach, and the water was hiding precisely where it was most difficult to find. This discovery changed everything about how scientists and engineers think about the moon's future. Not just as a subject of scientific study, but as a destination, a place where human beings might one day live and work for extended periods, sustained in part by resources available on the surface rather than carried expensively from Earth. Water, after all, is not just water. It is drinking water for human crews. It is oxygen when split by electrolysis, breathable air. It is hydrogen, the other product of that splitting rocket fuel. The moon's polar ice deposits, if they are as extensive as current evidence suggests, could be among the most strategically significant resources in the inner solar system. But that is a story for a later section of our journey. For now, let the discovery itself rest in your mind. The moon that for decades we thought we understood, dry, barren, exhaustively characterized, turned out to be hiding something fundamental. Something that had been there all along, patient in the darkness, waiting for an instrument sensitive enough and a question brave enough to find it. The cold and the dark were keeping something precious. Rest now, and in our next passage, we descend into the shadows where that discovery was waiting. There are places on the moon where the sun has never shone. Not simply places that are dark right now, waiting for the slow turning of the lunar day to bring light back to them. Not regions in temporary shadow, the way a valley on Earth might lie in shade during the morning hours before the sun climbs high enough to reach it. These are places where sunlight has not touched the surface in billions of years, perhaps since the moon itself formed. Places so geometrically sheltered, so perfectly angled away from the sun's low arc across the lunar polar sky, that they exist in a darkness as absolute and permanent as any in the solar system. They are called permanently shadowed regions, and within them, something extraordinary has been accumulating since long before the first living cell divided in Earth's primordial oceans. Ice. Water ice lying in the cold and dark, undisturbed and perfectly preserved, waiting with a patience that no living thing can fully comprehend. To appreciate how these regions exist, it helps to picture the geometry of the lunar poles. The moon's axial tilt, that small 1.5-degree lean we noted in our last section, means the sun, as seen from the lunar poles, never rises more than about 1.5 degrees above the horizon. It does not arc high across the sky the way it does from the equator. It simply skims, perpetually low, casting shadows of extraordinary length across the polar terrain. Near the poles, the lunar landscape is shaped by ancient impact craters, some small, some enormous, whose rims rise sharply above the surrounding terrain. A crater rim that rises even a few kilometers above the crater floor can be enough, at these latitudes, to permanently block every ray of sunlight from ever reaching the floor below. The geometry is unforgiving and precise. The sun skims the horizon. The crater rim interrupts the line of sight between the sun and the crater floor, and because the sun never rises high enough to look over the rim, the floor remains in permanent darkness, not for a season, not for a year, but for geological epochs. Scientists have mapped these permanently shadowed regions in detail using orbital spacecraft. Near the moon's south pole alone, they cover an area of perhaps 30,000 square kilometers, a region roughly the size of a small country, locked in eternal darkness, its surface temperatures hovering around -250 degrees Celsius. In that cold and that darkness, ice survives. But where did the ice come from? The moon has no indigenous water in any accessible sense. Its formation in the heat of the giant impact drove off most volatile compounds, including water. So the ice in the permanently shadowed regions arrived from elsewhere, delivered, over billions of years, by the steady rain of comets and water-bearing asteroids that has bombarded the inner solar system throughout its history. When a comet strikes the moon, the impact releases enormous energy, vaporizing the comet's ice and the surrounding rock almost instantly. Most of this water vapor disperses into space. But some fraction of it, perhaps a few percent, survives the impact in molecular form and begins to migrate across the lunar surface, hopping from one location to another as individual water molecules are warmed by sunlight and released, then drift until they land somewhere cooler and stick for a while, then are released again. This migration is a slow, random walk across the lunar surface. Most water molecules eventually reach a sunlit region and are dissociated by ultraviolet radiation, their hydrogen and oxygen atoms lost to space. But some, a small but steady fraction, find their way to the poles. And once a water molecule drifts into a permanently shadowed crater, it lands on a surface so cold that it has essentially no energy to escape. It sticks permanently. Over billions of years, molecule by molecule, impact by impact, a slow accumulation has taken place in the dark. The LCROSS impact in 2009 confirmed that water ice exists in these shadowed craters, but it was only the beginning of our understanding of how much ice might be there and in what form. Subsequent missions have refined the picture considerably. NASA's Lunar Reconnaissance Orbiter has mapped the permanently shadowed regions in extraordinary detail, measuring their temperatures, their surface reflectivity, and the distribution of hydrogen-bearing material across the polar regions. India's Chandrayaan-1 spacecraft carried a NASA instrument called the Moon Mineralogy Mapper, which detected the spectral signature of water and hydroxyl molecules not just in permanently shadowed regions, but across the broader lunar surface, suggesting that water exists in the lunar soil in small amounts across much wider areas than the polar cold traps alone. In 2020, observations from NASA's SOFIA Airborne Observatory, an infrared telescope mounted in a modified Boeing 747, detected water molecules in Clavius crater near the lunar south pole, in a location that receives sunlight. This suggested that water on the moon is more widespread and more varied in its distribution than even the cold trap model fully explained. The picture that has emerged is one of a moon that is not simply dry with a few pockets of polar ice, but a world with a complex water cycle of sorts, water delivered by impacts, migrating across the surface, concentrating in cold traps, potentially being released and redistributed by new impacts, and existing in trace amounts bound within mineral structures across the broader surface. The permanently shadowed craters near the lunar south pole have become, in recent years, among the most intensely studied real estate in the solar system. Not because of their scientific interest alone, though that interest is considerable, but because of what their ice represents for the future of human exploration. Water ice in accessible polar craters means that a lunar base near the South Pole would have access to one of the most essential resources for human survival, without needing to ship it from Earth. The economics of space exploration are dominated by the cost of lifting mass out of Earth's gravitational well. Every kilogram of water carried from Earth to the moon requires burning enormous quantities of rocket fuel. Water found on the moon and used on the moon costs a fraction of that. But the value of lunar ice goes beyond drinking water. Water can be split by electrolysis into its component elements, hydrogen and oxygen. Oxygen can be used for life support, giving astronauts breathable air. Hydrogen and oxygen together in their liquid forms are among the most powerful rocket propellants known, the same combination used by the engines of NASA's Space Launch System. Lunar ice, therefore, is not just water. It is potentially rocket fuel, produced on the moon from local resources, available to refuel spacecraft headed deeper into the solar system. Some scientists and engineers speak of the moon's polar ice deposits as the oil fields of the space age, a strategic resource that could underpin an entire economy of cislunar and deep space exploration. And yet, for all the practical significance of what lies in those shadowed craters, there is something beyond strategy that deserves a moment of quiet attention. The ice at the lunar poles is old, extraordinarily old. Some of it may have arrived during the late heavy bombardment, that intense period of cometary and asteroid impacts that occurred roughly 3.9 billion years ago. Water molecules that were once part of a comet formed in the cold outer reaches of the early solar system, that traveled for billions of years in the darkness of interplanetary space, that survived the impact with the moon and the long random walk to the poles, and that have been sitting in the frozen dark ever since. That water has been waiting in the shadow longer than the oldest fossil on Earth, longer than the oldest ocean sediment, longer than any rock on Earth's surface that has survived intact. When future explorers drill into the floors of the permanently shadowed craters and extract that ice, they will be handling material that is as old as the solar system itself. Water that has never been liquid on the moon, never been breathed, never been touched by any living thing. Ancient, patient, perfectly preserved. The shadow has been keeping its secrets for a very long time. But the lights are coming, slowly, carefully, on timelines that stretch years and decades into the future. Human beings are planning their return to the moon, and this time they are heading for the poles, for the ice, for the shadowed craters and the ancient water and the possibility of something that has never existed before. A permanent human presence on another world. Rest in that stillness, the cold, the dark, the ancient ice waiting in the shadow. The future is heading toward those craters, quietly and with great purpose, as we will discover next. More than half a century passed. The last human footprints were pressed into the lunar dust in December 1972. When Apollo 17 astronauts Eugene Cernan and Harrison Schmitt climbed back into their lunar module and lifted off from the Taurus-Littrow Valley. Cernan, the mission commander, was the last to board, pausing for a moment on the ladder, looking back at the surface he was leaving, aware that this was a threshold of some kind. He spoke a few words, a quiet acknowledgement that humanity was leaving but would return. It has been more than 50 years. The return has not yet happened, but for the first time since those final Apollo footsteps, it is no longer a distant aspiration or a political promise disconnected from hardware and timelines. The infrastructure is being built, the rockets exist or are being built, the suits are being designed, the landing systems are in development. The destination has been chosen, not the equatorial plains of the Apollo era, but the South Pole, where the permanently shadowed craters hold their ancient ice. Humanity is going back to the moon, and this time the plan is not to visit. The program carrying this ambition has a name drawn from Greek mythology. Artemis, the twin sister of Apollo, goddess of the moon in the ancient Greek pantheon. The name was chosen deliberately with an awareness of its resonance. Apollo went to the moon in the 1960s and 1970s. Artemis will go back, and among the astronauts it carries to the lunar surface will be the first woman and the first person of color to walk on another world. The Artemis program represents a different philosophy of space exploration than the one that drove Apollo. Apollo was a sprint, a focused, urgent dash to a single goal, driven by geopolitical competition, sustained by the concentrated force of national will and almost unlimited funding, and concluded once the goal was achieved. It was extraordinary, it was historic, and it ended with nothing permanent left behind except footprints and equipment and 6 descent stages sitting quietly in the lunar dust. Artemis is designed to be something else. Not a sprint, but a sustained campaign, a methodical international effort to establish a permanent human presence near the lunar South Pole, building infrastructure that will enable not just visits but habitation. Not just science but industry. Not just exploration but the beginning, tentative and uncertain but real, of human civilization beyond Earth. The architecture of the Artemis program reflects this long-term ambition. At its foundation is the Space Launch System, a heavy-lift rocket taller than the Statue of Liberty, capable of sending large payloads beyond Earth orbit. Above it sits the Orion spacecraft, which will carry astronauts from Earth to lunar orbit, a capsule more sophisticated than the Apollo command module, designed for longer missions and more complex operations. But unlike Apollo, Artemis does not plan to send astronauts directly from Earth orbit to the lunar surface and back. Instead, a key component of the architecture is the Gateway, a small space station planned for orbit around the Moon, serving as a staging point for lunar surface missions, a laboratory for science conducted in the unique environment of cislunar space, and a waypoint for future missions headed deeper into the solar system. The Gateway will not be built or operated by NASA alone. Space agencies from Europe, Canada, Japan, and other partner nations are contributing modules, systems, and expertise. The International Space Station demonstrated that humans can live and work in space for extended periods when nations cooperate. The Gateway extends that model to the vicinity of the Moon. From the Gateway, smaller landers will carry astronauts down to the lunar surface, to the South Pole, to the ice-bearing craters, to the terrain that was entirely unexplored during the Apollo era. These surface missions are planned to last not hours or days but weeks, long enough for meaningful geological fieldwork, for resource prospecting, for the kind of sustained scientific investigation that brief Apollo landings could only hint at. The commercial dimension of Artemis marks perhaps the sharpest departure from the Apollo model. In the 1960s, NASA designed and built almost everything itself, or contracted traditional aerospace companies to build specific components to NASA specifications. The agency was the customer, the designer, the operator, and the owner of all the hardware. Artemis operates differently. NASA has contracted commercial companies, most notably SpaceX, whose Starship vehicle has been selected as the initial human landing system, to develop and operate lunar transportation services, much as commercial airlines operate passenger services under regulatory oversight rather than government ownership. SpaceX's Starship is a vehicle unlike anything that has carried humans to space before. Fully reusable, enormous in its payload capacity, designed for rapid turnaround and frequent flight, it represents a fundamentally different approach to the economics of spaceflight. A Starship variant, refueled in Earth orbit by other Starship tanker flights, is planned to carry Artemis astronauts from the Gateway down to the lunar surface and back. Other commercial companies are developing smaller lunar landers, robotic surface missions, and eventually surface infrastructure under NASA's Commercial Lunar Payload Services program. Rovers, power systems, communication relays, even early versions of habitat structures, all being developed under commercial contracts, with NASA as one customer among potentially several. The Moon is becoming, in a carefully considered and still preliminary way, a commercial destination as well as a scientific one. Several nations beyond the United States are also planning lunar missions in the coming years and decades. China has conducted an impressive series of robotic lunar missions: Chang 4's Far Side landing, Chang 5's successful sample return in 2020, bringing back lunar material for the first time since the Soviet Luna 24 mission in 1976. China has announced ambitions to land humans on the Moon before 2030 and has proposed a joint lunar research station with Russia near the South Pole, a potential counterpart to the American-led Artemis program at the same strategically significant location. India's Chandrayaan-3 mission successfully landed near the lunar South Pole in August 2023, the first spacecraft from any nation to land successfully in that region, confirming the viability of South Polar surface operations and adding to the scientific data about the environment that human missions will need to navigate. Japan, the United Arab Emirates, and several private companies have either conducted or are planning lunar landing missions. The moon, after the long quiet following Apollo, has become one of the most actively targeted destinations in space exploration, simultaneously the object of renewed scientific curiosity, national ambition, commercial interest, and long-term strategic planning. Beneath all of this activity, the rockets and the programs and the international rivalries and the commercial contracts, something simpler and more human is present. The same thing that was present when ancient astronomers mapped the moon's surface by candlelight. The same thing that was present when Kennedy made his improbable promise to Congress. The same thing that was present when Cernan paused on the ladder of the lunar module and looked back at the surface he was leaving. We are not finished with the moon. We have never been finished with it. It hangs above us with the same patient presence it has always had, the same face, the same craters, the same ancient light reflected from its surface down through the atmosphere to fall softly on sleeping cities and open oceans. It has been there for every night of human existence. It watched us when we were small and frightened and barely different from the other animals. It watched us build fires and cities and spacecraft. It watched 12 of us walk on its surface and come home. And it is watching now as we slowly, carefully, with great seriousness and no small amount of hope, begin to plan our return. Not to visit, not to plant a flag and come home. To stay. Rest in that intention. Something is being built slowly, carefully, across nations and decades, and the moon is waiting with the same patience it has always had. Next, we will imagine what it might look like to actually live there. Begin with a simple question. What does it actually take to keep a human being alive? Not comfortable, not productive, not happy or fulfilled or intellectually engaged, just alive in the most basic biological sense. Air to breathe at the right pressure and composition, water to drink, roughly 2 to 3 liters per day, food providing enough calories to sustain metabolic function. A temperature range narrow enough that the body's regulatory systems can maintain core temperature without failing. Protection from radiation energetic enough to damage DNA. Shelter from impacts, micrometeorites, in the lunar case, that would be harmless in an atmosphere but lethal in a vacuum. On Earth, all of these things are provided freely, invisibly, by the planet itself. The atmosphere handles the air and the pressure and much of the radiation shielding. The hydrological cycle provides fresh water. The biosphere provides food. The magnetic field deflects charged particles. The sheer bulk of the planet's atmosphere absorbs the micrometeorites that would otherwise reach the surface. On the moon, none of these things are provided. Every single one of them must be engineered, maintained, and sustained by human technology, operating in an environment that is actively hostile to human life in almost every measurable way. This is the fundamental challenge of building a civilization on the moon, and it is a challenge that engineers, architects, biologists, and mission planners are engaging with right now, with tools and knowledge that make the solutions, difficult as they are, genuinely conceivable. The first and most immediate problem is radiation. Earth's magnetic field and atmosphere together provide substantial shielding against 2 primary sources of radiation in space: solar energetic particles, which are bursts of charged particles released by solar flares and coronal mass ejections, and galactic cosmic rays, which are extremely high-energy particles originating from outside the solar system. The moon has neither a global magnetic field nor a meaningful atmosphere. Astronauts on the lunar surface are exposed to radiation levels roughly 2 to 3 times higher than those experienced by astronauts aboard the International Space Station, and far higher than anything encountered in ordinary life on Earth. During a major solar energetic particle event, a solar storm, radiation levels on the lunar surface can spike dramatically within minutes, potentially reaching doses dangerous to human health if astronauts are caught in the open. The solutions being considered are several. Underground habitats, either tunnels excavated into the lunar regolith or natural lava tubes, hollow underground passages created by ancient volcanic activity whose ceilings can be tens of meters thick, would provide substantial radiation shielding, without requiring the energy cost of manufacturing shielding material from scratch. The regolith itself, piled over pressurized habitat structures, is an effective radiation shield. Even 2 or 3 meters of lunar soil overhead reduces radiation exposure to levels broadly comparable to living on Earth. Lava tubes are particularly intriguing. Lunar lava tubes, formed billions of years ago when volcanic activity was still occurring, are thought to exist across significant portions of the near side. They may be enormous, potentially hundreds of meters in diameter and kilometers in length, providing ready-made underground spaces large enough to enclose entire towns, protected from radiation, micrometeorites, and the extreme temperature swings of the lunar surface by the rock overhead. Temperature presents its own formidable challenge. The lunar surface experiences temperature swings of extraordinary magnitude. In direct sunlight, surface temperatures rise to around 127 degrees Celsius. In the lunar night, which lasts approximately 2 Earth weeks, temperatures plummet to around -173 degrees Celsius. At the poles, in permanently shadowed craters, even colder still. A habitat on the lunar surface must be insulated against these extremes, maintaining internal temperatures comfortable for human habitation, regardless of whether the sun is blazing overhead or the 2-week night has descended. This requires sophisticated thermal control systems, careful selection of habitat location, and insulating materials capable of handling a temperature differential of 300 degrees Celsius between outside and inside. The South Pole, interestingly, offers an advantage here. Certain elevated locations near the lunar South Pole, the peaks of crater rims and ridgelines, receive near-continuous sunlight because the sun skims so low on the horizon that elevated terrain catches it even when the valleys below are in shadow. These peaks of eternal light, as they are sometimes called, offer something unavailable almost anywhere else on the moon, a consistent, reliable source of solar energy, with none of the 2-week darkness that would require massive battery storage or nuclear power systems to bridge. A habitat at a peak of eternal light, with access via rover or tunnel to the permanently shadowed craters a few kilometers away where ice waits in the cold. This geography is why the lunar South Pole has become the focus of so much planning and ambition. The water from those shadowed craters, as we explored in our last section, is foundational to everything else. Electrolysis, splitting water into hydrogen and oxygen using electrical power from solar panels or nuclear reactors, provides both breathable air and rocket propellant. Oxygen extracted from lunar regolith through heating and chemical processes can supplement the supply. The regolith also contains useful quantities of silicon, aluminum, iron, titanium, and calcium, raw materials from which solar panels, structural components, and construction materials can potentially be manufactured using robotic systems powered by local energy. This concept, using local resources to reduce or eliminate dependence on supplies from Earth, is called in situ resource utilization, and it is considered essential to any sustainable long-term human presence on the Moon. The cost of shipping material from Earth's surface to the lunar surface is staggering, thousands of dollars per kilogram, even with the most efficient launch systems currently available. A lunar settlement that must import everything it needs from Earth will always be dependent, fragile, and enormously expensive. A lunar settlement that can manufacture most of what it needs from local materials is something fundamentally different. Something self-sustaining, something permanent. Food is perhaps the most human of the challenges. Caloric nutrition can be provided by stored supplies in the short term, as it is for astronauts on the International Space Station. But a permanent settlement requires food production, and food production requires growing things, which requires light, water, soil, or a soil substitute, and the management of a biological system in an environment that has never hosted biology of any kind. Lunar greenhouses, pressurized, artificially lit growing spaces where plants can be cultivated in hydroponic or aeroponic systems, are a practical near-term solution. Plants grown in this way provide not just food but psychological benefit, air refreshment, and water recycling. The psychological importance of greenery in an otherwise sterile and enclosed environment is not trivial. Human beings evolved in landscapes of living things. The absence of any growing, living, green thing from the immediate environment has measurable effects on well-being in confined spaces. Later, more ambitious visions include the possibility of growing food in large enclosed spaces, perhaps within lava tubes, where the scale of the enclosed environment makes something closer to a genuine ecosystem conceivable. Not a replacement for Earth's biosphere, but a beginning, a managed pocket of life in a lifeless world. Imagine it for a moment not as an engineering problem, but as a place. A settlement near the lunar South Pole, underground mostly, carved into the regolith or sheltered within an ancient lava tube. Pressurized corridors connecting modules where people sleep, work, eat, exercise. A greenhouse module where plants grow under artificial light and the air smells faintly of soil and green things. Windows, or rather screens, displaying real-time camera feeds from the surface, because actual windows in a pressurized underground habitat are structural vulnerabilities, showing the stark, beautiful landscape of the lunar South Pole, lit by a sun perpetually low on the horizon. Outside, rovers move between the habitat and the ice mining operations in the shadowed craters. A power station on a nearby ridge harvests sunlight that never quite sets. A small landing pad awaits the next supply mission from Earth, or perhaps the next flight to the gateway station in orbit above. People live here, work here, perhaps, eventually, are born here. It is not a comfortable life in the ordinary sense. It is a life defined by its constraints, its dangers, its extraordinary remove from the familiar world of Earth. But it is a life on another world, the first sustained human presence beyond the planet where our entire species has lived for its entire existence. That is not a small thing. It is, in fact, one of the largest things our species has ever done. Let that vision rest softly in your mind as you drift. A light in the darkness of the South Pole, human, warm, alive. And yet, even as we build toward that future, the moon itself is slowly, quietly leaving us. It is happening right now. Not quickly, not in any way that any instrument available to the naked eye could detect. Not in any way that will matter to you, or to your children, or to any generation of human beings who will ever walk this earth. But it is happening with a precision and a consistency that science has measured down to the millimeter, and it has been happening without pause since the moon first settled into its orbit more than 4 billion years ago. The moon is living. Every year it moves approximately 3.8 centimeters farther from Earth. Every year the distance between our planet and its companion grows by roughly the width of your hand. It is the slowest departure imaginable, a retreat so gradual that in an entire human lifetime, the moon will have moved away by only about 3 meters, less than the height of a ceiling. Imperceptible by any ordinary measure. And yet, given enough time, 3.8 centimeters per year becomes something profound. We know this number with remarkable confidence, and the way we know it is one of the more elegant stories in the history of scientific measurement. When Apollo astronauts visited the moon between 1969 and 1972, they left several pieces of equipment behind. Most of it, the descent stages, the scientific instruments, the rovers, was practical hardware that served its purpose and was then abandoned. But among the items placed on the lunar surface with particular care were small arrays of retroreflectors, panels studded with corner cube prisms designed to reflect light directly back toward its source, regardless of the angle at which it arrives. These retroreflectors were placed there specifically so that scientists on Earth could bounce laser pulses off them and measure the time it takes for the light to return. Light travels at approximately 299,792 kilometers per second. By measuring the round-trip travel time of a laser pulse with sufficient precision, to within a fraction of a nanosecond, scientists can calculate the distance to the moon with extraordinary accuracy. This technique is called lunar laser ranging, and it has been practiced continuously since the Apollo era. Observatories in several countries regularly fire powerful laser pulses at the lunar retroreflectors and time the returning signal. The data accumulated over more than 5 decades of these measurements has built a picture of the moon's orbital evolution with a precision that no other method could approach. The answer is unambiguous. The moon is receding at 3.8 centimeters per year, not approximately, not on average across geological epochs. Right now, measurably, confirmably, every year the number in the dataset grows by 3.8 centimeters. The mechanism driving this retreat is the same one we explored when we discussed the tides. Earth's rotation carries the tidal bulge, that slight deformation of the oceans and solid Earth caused by the moon's differential gravitational pull, slightly ahead of the moon's position in its orbit. The moon's gravity pulls back on this leading bulge, trying to align it, and this creates a braking force on Earth's rotation. Earth slows very slightly every year. But angular momentum must be conserved. The total angular momentum of the Earth-Moon system cannot simply disappear. Physics does not permit it. The rotational momentum bled away from Earth's spin has to go somewhere. It goes to the moon. The same gravitational interaction that breaks Earth's rotation gives the moon a tiny forward push in its orbit, accelerating it very slightly, which in the counterintuitive mathematics of orbital mechanics causes it to move into a higher, larger orbit. A higher orbit means a greater distance from Earth. The tides are not just pulling at the oceans and slowing Earth's spin. They are, through the exquisite bookkeeping of angular momentum conservation, pushing the moon away. Every wave that breaks on every shore, every tidal current that flows through every strait and channel, every slight deformation of Earth's solid body under the moon's gravitational influence, all of it contributes, in the most infinitesimal way, to the moon's slow recession. The ocean's breathing is the moon's departure. To feel the full weight of this, it helps to run the numbers backward. If the moon is currently receding at 3.8 centimeters per year, then in the past it was closer. Running the clock backward through geological time, accounting for the fact that tidal forces are stronger at shorter distances, which means the early recession rate was faster than it is today, brings us to a picture of the early Earth-Moon system that is startling in its difference from what we know today. In the first few 100 million years after the moon's formation, it may have orbited at a distance of perhaps 20 to 30,000 kilometers, compared to the current average of 384,400 kilometers. At that distance, the moon would have appeared 15 to 20 times larger in the sky than it does today. Its tidal forces on Earth would have been hundreds of times stronger. The tides on early Earth were not the meter-scale oscillations of our modern oceans. They were enormous, potentially kilometers high, sweeping vast distances inland with each cycle. These ancient supertides were likely a significant feature of early Earth's environment, shaping coastlines, stirring the oceans, possibly contributing to the chemical complexity of the environments where life first emerged. The moon that first formed was, in every sense, a more dramatic and more violent presence than the gentle companion we know today. Running the clock forward tells an equally striking story. At 3.8 centimeters of recession per year, and assuming that rate continues, which it will at some gradually decreasing pace, for as long as Earth's oceans exist, the moon will grow progressively more distant. In 1 billion years, it will be measurably farther away. In several billion years, the difference will be significant enough to affect the geometry of solar eclipses. The moon will appear smaller in the sky than the sun, and the era of perfect total solar eclipses, which we currently inhabit, will end. We touched on this in our second section. The eclipse coincidence, that perfect visual matching of moon and sun as seen from Earth, is temporary. We live in its last era. Future inhabitants of Earth billions of years hence will know solar eclipses only as annular events, the moon too small to fully cover the sun, leaving a ring of sunlight around its silhouette. Beautiful perhaps, but different. The totality that reveals the corona, that plunges the landscape into sudden darkness, that stops birds mid-song and drops the temperature several degrees in seconds, that will be gone. The moon will still be there, it will still be visible, still full, still crescent, still rising and setting in its familiar phases. But it will be smaller, more distant, a little less overwhelming in its presence. The relationship between Earth and Moon is not static, it never has been. It is an evolving dynamic, a slow, patient drift apart that began at the moment of the Moon's formation and will continue until forces far beyond either world bring it to an end. There is something quietly melancholy about this, if you let yourself feel it. The moon as we know it, this particular size, this particular distance, this particular balance of tidal force and gravitational steadiness and perfect eclipse geometry, is not a permanent feature of the universe. It is a phase, a long phase to be sure, extending across billions of years in both directions from our present moment, but a phase nonetheless. We exist in a specific window of the moon's history, the window when it is close enough to stabilize Earth's axis and drive meaningful tides, but far enough away that its tidal forces are not overwhelming. The window when its apparent size matches the sun's so perfectly that total solar eclipses exist. The window when its surface is accessible to human technology, its polar ice deposits reachable, its secrets answerable by the questions we are finally learning to ask. We are here at exactly the right moment. Or perhaps more accurately, we are here, and this is the moment we have. The laser pulses are still firing tonight from observatories in New Mexico and France and Apache Point, bouncing off the retroreflectors that Armstrong and Aldrin and the other Apollo crews placed in the lunar dust more than 50 years ago. The returning light is detected, timed, recorded. The data point is added to a data set that stretches back across half a century. 3.8 centimeters this year. 3.8 centimeters last year. 3.8 centimeters year after year after year, as the moon slowly, patiently, imperceptibly continues its ancient journey away from the world that made it. Let that slow movement carry you into stillness. The moon drifts and time drifts with it, and in our next passage we look to the far future when the moon will be too distant to perfectly cover the sun one last time. Every total solar eclipse begins the same way. Slowly, almost imperceptibly, a small notch appears at the edge of the sun, a bite taken out of the solar disk by the approaching moon, invisible without proper eye protection, easy to miss if no one tells you to look. For the first hour or so, the eclipse is a private event happening in plain sight. The world continues as normal, birds sing, traffic moves. The light seems unchanged, or nearly so. Then gradually the notch becomes a crescent. The sun shrinks, and the light begins to behave strangely. It does not simply dim the way it dims when clouds pass overhead. It changes quality. The shadows cast by trees and buildings become sharper, crisper, as if the world has been redrawn with a finer pen. Colors shift subtly toward the cool end of the spectrum. The air begins to feel different, a few degrees cooler, a change just perceptible on exposed skin. Animals notice before most people do. Birds begin to roost. Nocturnal insects start to stir. Bees return to their hives. Dogs grow restless. Something is wrong with the light, and every creature that evolved under it recognizes the wrongness even without understanding it. And then the last sliver of sun disappears behind the moon, and the world changes completely. Totality is unlike anything else in nature. The word is inadequate. It suggests simply the condition of being total, of something being complete. But what happens during totality is not merely the completion of an eclipse. It is the transformation of the entire visible world into something no human being is evolutionarily prepared for. The sky goes dark, not the soft dark of dusk, which comes gradually and carries the color of sunset with it. This darkness arrives in seconds, a shadow racing across the landscape at over 1,000 kilometers per hour, a wall of night sweeping over you before your eyes can fully adapt. Stars appear in the middle of the day, planets become visible. The horizon glows in all directions with the orange light of distant regions still in sunlight, as if you are standing in the center of a sunset that circles the entire world. And at the center of the darkened sky, where the sun was a moment ago, there is something that photographs never quite prepare you for. The corona. The sun's outer atmosphere, invisible in ordinary daylight, revealed in totality as a luminous, irregular halo of pearlescent light extending outward from the black disk of the moon, streamers and loops and delicate tendrils of superheated plasma, structured by magnetic fields, each eclipse revealing a different configuration because the sun's corona changes over its 11-year activity cycle. It is, by the account of almost everyone who has stood beneath it, one of the most overwhelming experiences available to a human being on Earth. And it exists only because, right now, the moon is exactly the right size and exactly the right distance to cover the sun almost perfectly. Not too large so that it would cover too much of the corona, not too small so that blinding photospheric light would prevent the corona from being visible at all. Exactly right, the coincidence of 400 and 400, which we explored early in our journey, playing out in the sky above you in minutes of breathtaking totality. This will not always be possible. We have followed the moon's slow recession throughout our journey, that 3.8 centimeter retreat per year, measured by laser ranging, accumulated over billions of years into a distance that has already grown from the moon's initial close orbit to its current 384,400 kilometer average. And that retreat will continue. As the moon moves farther from Earth, its apparent size in the sky shrinks. Not quickly, not in any way that any human generation will notice, not in any timescale that affects the planning of eclipse chasers or the predictions of astronomers working on human timescales. But over millions of years, the change is real and cumulative. There will come a point, geologists and astronomers estimate it at somewhere between 600 million and 1 billion years from now, when the moon's apparent diameter will no longer be sufficient to completely cover the solar disk during an alignment. The moon will pass in front of the sun and cover most of it, but a ring of sunlight will remain visible around the moon's silhouette. This type of eclipse already occurs today. It is called an annular eclipse from the Latin word for ring, and it happens when the moon is near the far end of its elliptical orbit, slightly more distant than average, slightly smaller in apparent size, insufficient to fully cover the sun. Annular eclipses are beautiful. They are impressive. The light dims, the sky changes, the ring of fire around the moon's dark silhouette is visually striking. But they are not totality. The corona cannot be seen. The diamond ring effect does not occur. The stars do not appear. The darkness does not descend. When the moon's recession has progressed far enough that no alignment can produce totality, when the moon is always too small, even at perigee, to fully cover the sun, the era of total solar eclipses on Earth will be over, forever. The last total solar eclipse. It is a strange thing to contemplate, not because it will happen soon, it will not on any time scale that carries human meaning, but because it will happen at all. Because the thing we take for granted, the existence of total solar eclipses, one of the most extraordinary spectacles in the natural world, is contingent, temporary. The product of a specific moment in the moon's orbital history that will eventually pass and not return. The first total solar eclipse occurred billions of years ago, when the moon was so close that it covered the sun enormously and completely, the corona barely visible around the overwhelming lunar disk. As the moon receded, the perfect alignment emerged, the ratio converging toward 400 and 400 as moon and sun reached their current apparent equivalence. And as the moon continues to recede, that perfect ratio will diverge again, the moon shrinking to less than the sun's apparent size, total eclipses becoming annular ones, and then the moon becoming simply too small to produce any dramatic central alignment at all. We are living in the sweet spot, the narrow band of geological time when the numbers align, when the coincidence is at its most precise, when a human being can stand in the path of a total solar eclipse and look up and see the corona with naked eyes and feel, in the most visceral possible way, the scale and beauty and strangeness of the solar system they inhabit. Every total solar eclipse that occurs from now until the last one is a gift of timing, a consequence of being alive in this particular era rather than one a billion years earlier or a billion years later. The orbital relationship between Earth and Moon is also changing in subtler ways that extend beyond eclipse geometry. As the Moon recedes, its tidal influence on Earth gradually weakens. The tides, already diminished from their ancient supertidal peaks, will continue to moderate. Earth's axial stabilization, provided by the Moon's gravitational influence, will remain effective for billions of years, but as the Moon moves farther away, the strength of that stabilizing force will slowly decrease. The slow lengthening of Earth's day, driven by tidal breaking, will continue, though as the Moon recedes and tidal forces weaken, the rate of that lengthening will gradually slow as well. The Earth-Moon system is winding down, not catastrophically, not dramatically, but with the same patient, inexorable quality that characterizes all of the Moon's interactions with our world, slowly, over timescales that require the full depth of geological perspective to appreciate. The relationship that was forged in violence 4.5 billion years ago, that shaped Earth's oceans and steadied its axis and lit the nights of every living thing that ever existed on this planet, is gradually, gently loosening. But not yet. Tonight, the Moon is where it has always been, familiar, steady, patient, rising as it has risen for every night of human existence, casting its soft light through your window, across the sleeping landscape, over the ocean still breathing to its rhythm. Tonight, if the sky is clear, you could look up and see that ancient face, the craters and highlands and dark Maria, all exactly where they have always been, and know that what you are seeing is not permanent. That the Moon will look slightly different to the humans of 1,000,000 years from now, and more different still to those of 100 million years from now, and that the era of perfect total solar eclipses is a window that time is slowly closing. But that window is open now, and the Moon is there. Let the quiet of that thought settle around you like the last light of an eclipse fading. We are here now in the window, and in our final passage, we will look to the most distant future of all, when even this long story comes quietly to its end. Let everything go quiet now. The journey we have taken together has moved through fire and collision, through ancient cooling and the slow birth of oceans, through the footsteps of 12 human beings on another world, and the patient measurements of laser light bouncing back from lunar dust. We have watched the Moon shape the tides and steady the seasons and guard the conditions that allowed life to grow from a single cell into everything that has ever lived and breathed and wondered on this planet. Now we arrive at the end of the story. Not the end of the Moon, not the end of Earth, but the end of the relationship as we know it, the final chapter of a partnership that has lasted longer than the oldest rock on Earth's surface, longer than the first ocean, longer than the first breath of oxygen in the atmosphere. A chapter written not in years or centuries, but in billions of years, in the patient language of orbital mechanics and stellar evolution, and the slow unwinding of the universe's most enduring arrangements. Come with me one last time into the deep future. 1 billion years from now, the sun will be approximately 10% more luminous than it is today. This is not a dramatic change on any human timescale, but on geological timescales, it is enormous. The sun, like all stars of its type, gradually brightens as it ages, the product of slow changes in the fusion reactions at its core, where hydrogen is steadily converted to helium, altering the density and pressure of the solar interior in ways that push the outer layers slightly outward and increase the total energy output. A 10% increase in solar luminosity will have profound consequences for Earth's climate. Current models suggest that within roughly 1 billion years, the increased solar energy input will push Earth's average surface temperature beyond the range that liquid water can persist over geological timescales. The oceans will not boil away overnight. The process will be gradual, unfolding over hundreds of millions of years, but the trend will be irreversible. Water will evaporate into the upper atmosphere, where ultraviolet radiation will break it apart into hydrogen and oxygen, the hydrogen escaping to space and the oxygen reacting with surface minerals. The great blue oceans that have covered most of Earth's surface for 4 billion years will slowly, steadily disappear. With the oceans gone, the tidal interaction between Earth and Moon loses its primary medium. Tidal forces will still act on Earth's solid body, the solid Earth tides, which currently exist alongside the ocean tides but are much smaller in magnitude, but the enormous energy dissipation that drives the Moon's recession and Earth's rotational slowing will diminish dramatically without liquid oceans to amplify it. The Moon's recession rate will slow. Earth's days will lengthen more slowly. The relationship between Earth and Moon will enter a new phase, quieter, less dynamic. The great tidal conversation that has defined them for billions of years, reduced to a murmur. Without liquid water, Earth's surface will transform. Plate tectonics, which depends in part on water acting as a lubricant in the subduction zones where oceanic plates descend into the mantle, may slow and eventually cease. Without plate tectonics, the carbon cycle that has helped regulate Earth's climate for billions of years will stop functioning. Carbon dioxide, released by volcanic activity, but no longer efficiently removed by the weathering of silicate rocks and the burial of organic material, will accumulate in the atmosphere. The greenhouse effect will intensify, temperatures will rise further. The surface of Earth will become something closer to the surface of Venus than the blue world we know, hot, dry, geologically quiet, wrapped in a thick and inhospitable atmosphere. 5 billion years from now, the Sun's story will be approaching its own conclusion. Having exhausted the hydrogen fuel in its core, the Sun will begin to fuse hydrogen in a shell around the core, causing the outer layers to expand dramatically. The Sun will swell into what astronomers call a red giant, growing to perhaps 100 times its current diameter, its surface temperature dropping and reddening even as its total luminosity increases by orders of magnitude. In the red giant phase, the Sun will expand outward toward the inner planets. Mercury and Venus will almost certainly be engulfed, swallowed by the expanding solar atmosphere, their orbits lying within the bloated star's outer layers. Earth's fate is less certain. Current models suggest Earth may just barely escape direct engulfment, its orbit having expanded slightly due to the Sun's mass loss during its red giant phase. But even if Earth's physical body survives, its surface will be scoured by temperatures of hundreds of degrees, any remaining atmosphere stripped away by the intense stellar wind, any trace of the world we know reduced to bare, scorched rock. The Moon, in whatever orbit it occupies by this point, slightly farther than today, the recession having continued through the billions of intervening years, will share this fate. The same solar wind that strips Earth's last atmosphere will gradually erode the Moon's surface, implanting particles in the regolith, slowly changing its composition. The solar tidal forces, enormously amplified by the Sun's expanded size and increased luminosity, will alter the orbits of everything in the inner solar system. The familiar Earth-Moon system, the partnership forged in the violence of the giant impact, maintained through billions of years of tidal interaction, responsible for everything from the tides to the stability of the seasons to the existence of complex life, will be unrecognizable. And yet, in the deep future that these timescales imply, something remarkable will still be true. The footprints in the Sea of Tranquility will still be there, buried perhaps under billions of years of micrometeorite gardening, covered by a thin accumulation of regolith that has slowly worked its way over them, but preserved in some form in the lunar rock. A chemical and physical record of the moment 5 billion years earlier, when a small creature from a small blue planet crossed the void of space and stood on another world for the first time. The laser-ranging retroreflectors will still be there, their precise optical geometry perhaps degraded by cosmic ray bombardment over 5 billion years, but their physical presence unchanged. The descent stages of the 6 lunar modules will still be resting on the surface, their structures altered by the relentless environment of deep time but not erased. The moon will remember us even after everything else is gone. Come back now to the present. Come back to tonight, to this moment, to the breath moving slowly through your body and the weight of your body against the surface beneath you. Come back to the world that still has oceans and seasons and the 24-hour rhythm of day and night. The world where the moon rises every night and the tides breathe twice every day, and the total solar eclipses still occur, and 12 pairs of human footprints wait in the stillness of the sea of tranquility. You are here in the window, the long, extraordinary, improbable window in which a planet had the right companion at the right distance for the right duration to allow something as fragile and brief and remarkable as conscious life to emerge and look up and understand, even partially, what it owes to the silent world overhead. For 4 billion years, the moon has done its work without acknowledgement, without thanks, without any awareness on the part of the planet it serves that the service is being rendered. It simply orbits, steadily, faithfully, holding the axis steady, pulling the tides, lighting the darkness, keeping the long, slow conditions that life requires. Tonight, as you drift towards sleep, it is there. The same face it has always shown. The same craters that Galileo sketched by candlelight 4 centuries ago. The same dark plains that ancient people named seas. The same bright highlands that crystallized from a magma ocean more than 4 billion years ago. The same familiar patterns that have watched over every night of human existence since the first of us looked up and felt the pull of wonder. It does not know you are here. It does not know that the creatures it helped create have named it and mapped it and walked on it and measured its recession to the millimeter, and plan to go back and build homes in its southern shadows. But you know it is there. And perhaps that is enough. Perhaps that is, in fact, everything, that the universe arranged itself in such a way that matter could become aware of its own arrangements. That the debris from a 4 billion year old collision could, in time, become curious about its own origins. That the moon, which has never looked back at us in any conscious sense, has been seen and understood and quietly, deeply appreciated by the life it helped bring into being. For billions of years, the moon has shaped our oceans, steadied our world, guided our explorers, inspired our dreamers, and quietly protected the long, slow miracle of life itself. It hangs above you now, familiar and ordinary, pale and patient, exactly where it has always been. And without it, none of us would be here. Sleep well, the moon is keeping watch.